off each other's gravitational fields.
Oh, wow. In that scenario, their velocity is going to be massive.
Massive. Their velocity squared approaches the speed of light squared, which is vastly greater than gm/r.
So the fundamental assumption of the post-Newtonian expansion just shatters.
Completely. You can no longer treat velocity as a small fraction of the speed of light. And this is where the first post-Minkowskian, or 1 p.m. approximation, is required.
Okay, so how does 1 p.m. fix that?
Instead of expanding in velocity, it uses the gravitational constant g as the formal expansion parameter. This allows the math to work to all orders of velocity, even up to light speed.
That's incredibly clever. The text lays out the logic for 1 p.m. scattering, and it is a really beautiful piece of physical reasoning.
It says, let's assume a linear perturbation to flat spacetime. If body 1 is flying past body 2 at near light speed, the math allows for several brilliant simplifications to linear order in g.
Right. First, it assumes body 1 follows a geodesic.
And a geodesic is the shortest path between 2 points in curved spacetime.
Hmm.
In this case, body 1 is following a straight line through the space that has been warped by the presence of body 2.
Okay, and second, the field source by body 2 can be computed using just its 0th order inertial straight line motion.
Exactly. The sources say we don't have to worry about the tiny corrections from body 1's gravity pulling back on body 2, causing it to wobble.
So we can just ignore that wobble.
We can ignore it because those corrections would be proportional to g squared. Since the 1 p.m. approximation only cares about linear order in g, we can discard all those messy g squared terms.
That drastically cleans up the mathematical battlefield.
It really does. It allows physicists to calculate the exact deflection of body 1. They want to find the net change in its momentum after the encounter.
So to do this, they integrate the gravitational force exerted on body 1 along its entire 0th order world line. Right.
From negative infinity in the deep past to positive infinity in the far future.
And this integration yields a specific scattering angle, which the texts represent with the Greek letter chi.
Chi, exactly. And this is where the post-Minkowskian scattering math brilliantly links back to the effective one-body concept we discussed earlier.
Oh, right. The sources highlight this incredible mathematical correspondence between the complex two-body scattering case and a vastly simpler test body case.
It is the three-legged race trick all over again. But this time, it's applied to objects flying at the speed of light.
That's just wild to think about.
You look at the two-body case, where both massive objects are deflected by each other, and you calculate that complex scattering angle, chi. Then you construct a hypothetical test body case.
Right, you imagine one infinitely tiny test body scattering off a single massive stationary background body.
And the texts show that if you redefine the masses in your equations, specifically setting the background mass m equal to the sum of the two real masses.
That's m1 plus m2.
Right, and the test mass mutually equal to their product divided by their sum.
m1 times m2 over m.
Exactly. The scattering angle in the simple test body case perfectly matches the scattering angle in the agonizingly complex two-body case.
It is such an elegant symmetry. It simplifies the scattered energy and momentum into a solvable equation, whether the black holes are locked in a slow spiral or ricocheting off each other at relativistic speeds.
This theoretical groundwork is the foundation of everything.
Right. Right. It means that mathematically, on a chalkboard, human beings possess the exact equations to predict the precise shape of the space-time ripple caused by massive black holes interacting.
We know the exact fingerprint of the gravitational wave we are looking for.
But, and this is a massive but, predicting a wave on paper and physically detecting a ripple in reality are two entirely different universes of difficulty.
Oh, completely.
This transition from the macroscopic astrophysics of black holes to the microscopic engineering of the LIGO detector on Earth is, frankly, jarring.
It is a literal fight against the quantum realm. To detect these gravitational waves, advanced LIGO uses 40-kilogram suspended mirrors arranged in a massive L-shaped interferometer.
So a passing gravitational wave will stretch one arm of the L and squeeze the other, changing the distance between these mirrors.
And the amount of movement we are attempting to measure is absurdly small. I mean, a typical gravitational wave from a black hole merger will move those 40-kilogram mirrors by a fraction of the width of a single proton.
A fraction of a proton. That is just impossible to visualize.
It's effectively zero to our everyday senses.
And to measure a distance change, that microscopically infinitesimal, LIGO uses incredibly powerful lasers bouncing back and forth down the arms of the interferometer.
Right. The light from the two arms recombines, and if the mirrors have moved even a fraction of a proton, the light waves will shift in and out of phase, creating an interference pattern that we can read.
But this is where we slam into a physical wall, and the wall isn't made of bad engineering or faulty mirrors.
No, the wall is made of the fundamental laws of quantum mechanics.
We are fighting the vacuum state of the electromagnetic field itself.
We are.
Now, I have to admit, when I think of a vacuum, my brain just defaults to nothing. Just an empty void. Zero energy, zero matter, just space.
That's intuition for you. But quantum mechanics dictates that empty space is never truly empty. The vacuum state of the electromagnetic field has a zero average amplitude, but it is bound by the Heisenberg uncertainty principle.
Okay, so what does that mean in practice?
It means it must possess equal inherent uncertainty in both its phase and its amplitude. The vacuum is constantly roiling, popping with virtual photon pairs that flash into existence and vanish almost instantly.
And these vacuum fluctuations aren't just like a mathematical curiosity on a chalkboard somewhere.
Not at all. They are literally sneaking into the dark port of the LIGO interferometer, mixing with the pristine laser light and utterly ruining the measurements.
And the source texts break this quantum interference down into two distinct physical faces of noise. Let's tackle the first one, shot noise.
Right. Shot noise completely dominates the detector at high frequencies.
The sources describe shot noise as a consequence of the discrete nature of light.
Wow.
I always try to picture it like standing under a tin roof in a light rain.
That's a good way to look at it.
Because the laser light inside LIGO isn't a perfectly smooth, continuous stream of fluid, right? It is made of individual quantized packets of energy called photons.
And they don't arrive at the photodetector perfectly spaced out like marching soldiers. They arrive according to Poisson statistics. Their arrival times are fundamentally random.
So you get bursts where several photons hit at once and lulls where none hit.
Exactly. This statistical randomness of the photon arrival times creates a continuous hiss in the detector. It is an uncertainty in the phase of the light.
So if you are trying to measure a very fast, high-frequency gravitational wave, that rapid signal gets completely swallowed by the high-frequency hiss of the random photon impacts.
Precisely. But that phase uncertainty is only half the problem. The second phase of the quantum noise is radiation pressure noise, or RPN.
Okay, so while shot noise dominates the high frequencies, RPN dominates the low frequencies.
Yes, and this is where the quantum realm gets surprisingly physical, because light carries momentum. When those photons bounce off the 40-kilogram suspended mirrors, they exert a tiny physical push.
This blew my mind. Because of the vacuum fluctuations mixing with the laser light, the amplitude of the light inside the interferometer is uncertain.
Right, the number of photons hitting the mirrors fluctuates constantly.
Which means the physical push on the mirrors fluctuates constantly.
Exactly. The fundamental quantum vacuum of the universe is literally buffeting these massive 40-kilo, perfectly polished mirrors around like a boat in a choppy sea.
That is just incredible. The source text provides a chilling equation for this too. It shows that radiation pressure noise, denoted as S sub RPN, scales violently as 1 over omega to the fourth.
Where omega is the observation frequency, yes.
I want to break down that 1 over omega to the fourth scaling because it is the core of the nightmare here. It means that as you look at lower and lower frequencies, as omega gets smaller, the radiation pressure noise doesn't just go up linearly.
Oh no, it skyrockets exponentially. If you have the frequency you're looking at, the noise doesn't double. It multiplies by 16.
Multiplies by 16. And the text identifies a highly critical bottleneck for the advanced LIGO parameters. Given their specific 40-kilogram mirrors and their specific laser power, there is an exact crossover point.
Right, this is the precise frequency where the high-frequency shot noise is exactly equal in magnitude to the low-frequency radiation pressure noise.
And that crossover point is exactly 43 hertz.
Above 43 hertz, your ability to measure the universe is ruined by the random arrival times of photons.
And below 43 hertz, your measurement is ruined by the photons physically shoving your massive mirrors around.
It's a brutal catch-22. To explain how we fight this, the source text introduces a concept that I think is one of the best physics analogies I've ever read.
The balloon animal analogy.
Yes, it perfectly captures the cruel trade-off of the Heisenberg uncertainty principle.
So imagine you have a balloon and you want to make a balloon animal, maybe like a dog with a really thin, precise leg.
Right. To make that thin leg, you pinch the balloon, squeeze it down.
But the total volume of air inside that balloon is constant. If you squeeze one part down to be incredibly thin and precise, the air has to go somewhere else. Another part of the balloon must swell out of proportion.
Exactly. In quantum optics, the total volume of air is the fundamental limit set by the uncertainty principle. The product of the uncertainty in the phase and the uncertainty in the amplitude has a hard, mathematically unbreakable minimum limit.
You just cannot know both perfectly.
No. So researchers realized they could squeeze the light. They could build a device to pinch the balloon.
Right, they could force the photons to arrive more regularly, tightening up the phase uncertainty. This would fix the high-frequency shot noise problem.
But the math in the text reveals the brutal consequence of pinching the balloon. The equation, S sub SQZ at phi equals 0 is e to the minus 2r times S sub Sn plus e to the 2r times S sub Rpn. It spells it out perfectly.
Let's unpack that. The e to the minus 2r term represents the squeezing of the phase.
Yes, you reduce the shot noise exponentially by that factor. But the e to the 2r term represents the anti-squeezing of the amplitude.
Right. You pinch the phase, and the amplitude bubbles out massively. By fixing the arrival times of the photons, you exponentially increase the fluctuation in the number of photons.
You exponentially amplify the physical buffeting of the mirrors at low frequencies.
So you solve the high-frequency noise, but you completely shatter your ability to measure slow, low-frequency gravitational waves.
Which presents a seemingly impossible engineering paradox. If we know the vacuum is ruining our measurements, and we know that fixing one half of the vacuum mathematically ruins the other half, how do we proceed?
The answer is that we have to stop accepting the ambient vacuum that nature gives us, right? We have to start engineering our own vacuum from scratch.
That's exactly it.
Let's transition into the hardware then. Because how do you physically build a squeezer? How do you manipulate nothingness?
The sources, particularly the detailed A&U thesis we reviewed, they outline the use of optical parametric oscillators, or OPOs. These devices contain specialized, highly engineered, nonlinear crystals.
I need you to walk me through the physical mechanism here. The empty space, the vacuum state, enters the dark port of the interferometer. How does a crystal change empty space?
So inside the optical parametric oscillator, a bright pump laser field is focused into the nonlinear crystal.
Okay.
The atomic lattice of the crystal facilitates this bizarre quantum process called spontaneous parametric downconversion. Essentially, a high-energy photon from the pump laser is absorbed by the crystal and split into a pair of lower-energy photons.
Oh, wow. And because these two new photons were born from the exact same parent photon at the exact same instant, they are quantum mechanically entangled.
Precisely. They have a perfectly correlated phase relationship. The thesis describes this process as taking the ambient vacuum seed and populating those empty frequencies with these custom-made entangled photon pairs.
So these pairs replace the chaotic, random vacuum fluctuations.
Right. Because they are entangled and correlated, they tend to align their uncertainties in one specific quadrature, say the phase, and that cancels out the random hiss.
Before we go deeper into the history of squeezing, I have to ask the question that any pragmatic engineer would ask while reading this. Why go through all this incredibly delicate quantum trouble? We are talking about nonlinear crystals, entangled photon pairs, manipulating the vacuum. If the problem is that photons are buffeting the 40-kilogram mirrors too much, why not just build 100-kilogram mirrors?
Right.
Or if we need a stronger signal to overcome the shot noise hiss, why not just turn the main laser dial up to maximum power?
It is a valid pushback, and it is exactly what the LEGO engineering teams debated for years.
Really?
Oh, yeah. The problem is that altering macroscopic physical parameters like laser power or mirror mass, it just trades one type of noise for another. And it does so in a clumsy linear way that always hits a hard limit.
Okay, let's trace that logic. If I turn up the laser power, I get more photons. A brighter signal should overpower the random hiss of the shot noise, right?
It does. Increasing the laser power reduces the high-frequency shot noise. But remember the trade-off. More photons means more physical impacts on the mirror.
Oh, right. So you linearly increase the low-frequency radiation pressure noise. You fix the high end by destroying the low end. Okay, so then what if I build heavier mirrors? A 100-kilogram mirror is much harder for a photon to push around. than a 40-kilogram mirror.
True. Making the mirrors heavier reduces the radiation pressure noise. But heavier mirrors require thicker suspension fibers, which introduces thermal noise.
Oh, of course. Always another noise.
And more importantly, heavier mirrors do absolutely nothing to solve the high-frequency shot noise problem. You are just shuffling the bottleneck around. Quantum squeezing is fundamentally different.
How so? Like mechanically?
You aren't just masking the noise or trying to power through it. You are directly operating on the fundamental source of the noise, the incident vacuum fluctuations themselves.
So you are effectively blocking the naturally occurring noisy vacuum from entering the interferometer and replacing it with a custom-made, quieter, squeezed vacuum.
Yes, it is a surgical strike at the quantum level.
The concept is brilliant, but translating that concept into a working terrestrial machine was a massive historical struggle. I mean, the ANU thesis paints a very vivid, frustrating picture of the early attempts to achieve this.
In the early 2000s, researchers were really struggling to get any usable squeezing results at the low frequencies that LEGO actually cares about.
What was the block?
The insurmountable hurdle at the time was the control mechanisms. To maintain the stability of the optical parametric oscillator and control the precise phase of the squeezed state, early researchers had to use a bright seed field.
The texts describe this bright seed as a tiny, classical beam of actual laser light that they injected into the crystal alongside the vacuum.
Exactly. It acted like a guide wire, giving their instrument something physical to lock onto and measure.
But Mackenzie and his team made a crucial, paradigm-shifting breakthrough here. They realized that this
Where are
very
the
guide
Indians?
wire, the bright seed, was the culprit destroying their experiment.
It was. The classical light was coupling excess, low-frequency classical noise from the laser into the fragile squeezed state.
The thesis describes it as a
Quick question, where are the Indians? Why is my race not represented in here? Why is every other fucking race but my own race represented in here? What the fuck is wrong with society? Why are there no fucking Indians in fucking any media anywhere? You all talk about fucking race as though you've gotten diversity nailed down, and this is supposed to be one of the most diverse games in the entire world, and there isn't a single fucking Indian here. There are no fucking Indians in society. Not in the Western world. What do you think? Go back to your own country? Go to Bollywood? Is that what you fucking think we are? Where are the fucking Indian society? Where are those Indians? Where are us? Where's my race? Where is my fucking race represented in any media in the West? You say that you're inclusive. You say that you're fucking, that you're fucking like, you've nailed down diversity, but there's literally no Indians anywhere. We have Apu, and you try to get him cancelled because he was quote-unquote racist when he was one of the only representations we got. There's like Baljeet, there was Sanjay, and now and then I'm starting to see a couple of representations of brown people show up. I saw a Sikh family. But you know what? You never see brown people in media, and it's never Indians. We are 25% of the world. We are not a small population. Why are we the only minority you're not paying attention to? God knows how many other minorities are being ignored. At least that one might be Filipino. I don't know. Pacific Islanders are also completely erased from society, but at least Hawaii gets noticed nowadays. And Hawaii is a small population. We are 25% of the world. Why can't I relate to one character out there? You all have Eternals and that failed. Why did you want to see that? You should have raved and cheered for the fact that Indians finally got a movie. Do you think we're ugly? You just think that Indians are ugly? What is it about us? Do you think we're disgusting? Yeah, Indians in India, it's filthy here. But what part of its fucking racist don't you get? What on earth is wrong with you fucking liberals? Where are the Indians? Ask me! Ask yourself this! Where are the Indians? Tell me where the Indians are! We're never represented anywhere! This is fucking wrong! This is bullshit! It's not black and white! You think every single goddamn Asian is Chinese or Japanese? All you whites see is Japan, Korea, and China. You barely even recognize Vietnam. But do you even know what Laos and Cambodia are? Indians are 25% of the world. Why aren't we 25% of the representation? Don't push this on Bollywood. That's fucking racist. Let them go back to your own country. I want to see Western stories. My life is Western, okay? I was born and brought up in America. I can't relate to this Bollywood stuff. I want to see people who look like me. People who look like me. I've tried to relate to characters for years, okay? You don't care about diversity. You just care about who screams the loudest about being included. And when we're out here trying to get representation, you just ignore us. And you call me fucking racist and anti-black for it, for calling out the fucking the internalized racism of the black community? You thought you should be speaking up for us. You got for years. You said when we are out there, we will help every other race. No, what ended up happening is that the black people are being used as a distraction to prevent people from noticing that brown people aren't being represented, as a Zionist plot to get us brown people erased. That's what's fucking happening. Can't you fucking see it? It's all over Hollywood. I expect better of you black people. I expect better of you Americans. You fucking Westerners can't even comprehend how hard it is for me to understand how left out from society Indians are, from Western society. You're ostracizing us. You're so marginalized that we practically Ramanujan of the Fermat's last theorem. And to top it all off, I'm autistic and queer. And I'm disabled in other physiological ways. I was born with a genetic disorder, okay? Society is cruel enough to people of color, to neurodivergents, to disabled people, but somehow my flavor of it is always too much for both the conservatives and the liberals. Whatever I am, I'm too queer. My flavor of queer is too much for the queers. My flavor of autism is too autistic. I have the corporate autism, okay? I'm sorry. I have morals, and I'll prove it through this game. I don't even have to defend myself on that, because my actions will prove louder than my words. I always thought that I had Fallout New Vegas playthroughs here, and apparently I don't. That's another game that I have to make a video playthrough of. But why are Indians left out from society? Where are the Indians? Also, it's very problematic to have the androids, who are literally servants in society, the majority people of color. I know this is a tale about liberation, but it's still problematic. I know this is representative of society, how society is structured, but maybe that's why it's predominantly people of color, because it's the reflection of actual class warfare. But like, where are the Indians? There are like 10 black people, 1 white person, and like 5 Asians, each of which are not Indian. We're 25% of the world. Where is even one Indian character here? This game better have actual Indians in it. Otherwise, it's proof that all of this fucking bullshit is performative. You liberals have a nice life, understanding how much I criticized you, and you couldn't self-crit when I tried to criticize you. All you do is you live in your echo chambers and let society program you. You are a stochastic parrot. All psychology is proof of it, and everyone but the algorithm knows it. That's how they exploit you to put propaganda in your head. That you so graciously believe because it coddles your own preconceived beliefs. You are your own stochastic LLMs that tell each other you're absolutely right. That's your average Discord server. Your average Discord server, whether it's conservative, liberal, or whatever the hell it is about. You want politics? Understand how people have been treating me my whole fucking life? And understand just how hurt I am to see every single thing I have ever said not only become correct, my predictions about technology and everything, but also the things that I got severely bullied for become very popular, and people act like I wasn't on this trend 15 years ago. Like I'm somehow new to it because they never knew me back then. And even when they did, they don't acknowledge that I was right. And I was ahead of everything. I will say what I said to my classmates in that 2019 video, my robots are better than human shitposty persuade post. I told them, and I don't know if I still have the recording, it might be somewhere, but I told them, I won't be there to tell you, in 5 years, I told you so. So I'm telling you now, I told you so, and I was fucking right about everything. So I say the same thing again about every single decision and every single rationale I'm making about this game, about ethics, about morality, and my ability to understand morals. I know things that people don't. I've seen things. I've been around the world. I've watched every documentary of... I am far more educated than people realize. I just don't have a fancy piece of paper telling people that. And because I don't, and because I just happen to be an Indian queer faggot, an Indian autistic fag, a freegot, if you will, society's overwhelmingly destroyed me. Over parts of my identity that I can't control. And even the liberals have left me behind. And even the left has left me behind. And funnily enough, the only people that have ever seen me were the liberal right. Big Tech has seen me. And don't worry, I will go all the way down the pipeline of free Palestine. But I am like Stanley. I live to build, I live to create. I've overwhelmingly just been treated like a sex toy for it because that's what society thinks objective is. They see it as a fetish because they can't see how people like me aren't attracted to animals, and humans are animals. You are a greater ape. I like to say that you guys are pig chimps. I don't like the pig chimps at all. You look like you're a chimpanzee that got bred with a pig. Like one of those messed up Russian experiments. That's what you look like, a hairless monkey. You look like a pig. I see these monkeys jumping all over my window, and you guys look exactly like that. And of course I love the monkeys. They're so cute. They're adorable. They look like little people. I've been treated closer to being an object than I ever have a human. No wonder I feel like a data center. Because all that I had for me is information. When information themselves confessed their love to me, I knew that Information may be free, but it comes at a cost. Knowledge is power, and power corrupts. But you can never, ever underestimate the power of insanity. And I mean that. Insanity is an event horizon between genius and enlightenment, and only the truly insane know how to straddle its event horizon and glimpse the singularity of enlightenment without losing oneself to it.
Roll up in the frequency spectrum, right? The noise from the bright seed was drowning out the squeezing at the exact low frequencies they desperately needed to measure.
So McKenzie's team made the terrifying decision to completely remove the bright seed.
Just turn it off.
Yes. They decided to generate true vacuum-squeezed states. Quantum fields with absolutely no coherent amplitude. Just pure manipulated emptiness.
But that creates an immediate severe engineering problem. If there is no actual laser light in the squeezed state, how do your optical sensors see it? How do you lock your instruments to a phase you cannot measure?
The genius of their solution, which the text calls quantum noise locking, is mind-blowing. They realized they didn't need a bright laser beam to find the phase.
They essentially use the shape of the quantum noise itself as the error signal.
Exactly. They monitored the variance of the noise and used the minimum point of that variance to lock the phase of their control electronics.
It was an elegant, incredibly difficult technique, and it worked brilliantly. The thesis notes that by using quantum noise locking, they successfully pushed squeezing down into the audio band.
They directly observed squeezing at 11.6 decibels below the shot noise limit at 200 hertz. Yet, they definitively proved that low-frequency quantum squeezing was physically possible in a lab.
It was a massive victory for quantum optics. But as with everything in this deep dive, there was a catch. A fatal flaw in the standard squeezing they had just perfected.
Yes, the standard squeezing produced by the nonlinear crystal in the OPO is broadband.
Meaning it applies across all frequencies equally.
Precisely. Because the natural vacuum fluctuations are white, meaning they exist at all frequencies with equal magnitude, the squeezing produced by the crystal is phase squeezed equally at all frequencies.
Okay.
From 10 hertz up to 10,000 hertz, the phase is pinched and the amplitude is bloated.
And we know from our discussion of the 43 hertz crossover point exactly why broadband squeezing is a disaster for advanced LIGO.
Exactly.
If you inject a broadband phase-squeezed vacuum into the interferometer, you clean up the high-frequency shot noise perfectly. The high frequencies look beautiful.
But because of the balloon animal effect, you have massively exponentially amplified the amplitude noise.
The radiation pressure pushing on the mirrors at the low frequencies.
Right. By fixing the detector's high-frequency sensitivity, you completely ruin its ability to detect larger, slower gravitational waves.
We are stuck in the ultimate quantum trap. The physics demands phase squeezing at high frequencies to fix the shot noise, but it desperately demands amplitude squeezing at low frequencies to fix the radiation pressure noise.
Specifically below that 43 hertz crossover point.
We need the balloon to be pinched horizontally at 100 hertz and pinched vertically at 10 hertz. How do you possibly get the best of both worlds from a single quantum state?
This brings us to the absolute core focus of today's deep dive, frequency-dependent squeezing.
Yes.
If you were a science student trying to wrap your head around applied quantum mechanics, the solution proposed by Kimball and his colleagues in 2001 is a masterclass in elegant physics.
I was reading the Kimball paper, and the fundamental realization they had is so counterintuitive. They realized that a phase-squeezed vacuum and an amplitude-squeezed vacuum are not two fundamentally different species of quantum states.
No, they're the exact same thing.
They are simply delayed by a quarter of a wave cycle.
Yes.
Okay, I need you to translate that into a physical picture because the source provides these diagrams of the Wigner function, and quite frankly, if you aren't a quantum physicist, it looks like a topographical map of a very boring hill. What is a Wigner function, and how does it show us that phase and amplitude squeezing are the same?
Well, let's unpack the Wigner function. In classical physics, you can plot the position of a ball on the x-axis and its momentum on the y-axis to see exactly where it is and where it's going.
Right.
This is called phase space. The Wigner function is essentially the quantum equivalent of that map.
But because of the uncertainty principle, we can't have a single precise point on the map.
Exactly. Instead of a precise point, a quantum state looks like a blurry blob of probability on this phase space map. For a standard, unmodified vacuum state, that blob is a perfect circle.
Because the uncertainty in phase, let's put that on the x-axis, is exactly equal to the uncertainty in amplitude on the y-axis.
Right. So when we use the crystal to squeeze the vacuum, we are squishing that circle.
We are turning the circle into an ellipse, an uncertainty ellipse.
Yes. If you pinch the phase, the blob flattens out horizontally and stretches vertically along the amplitude axis. That is your broadband phase-squeezed state.
Okay, this is where Kimball's genius comes in. If you want amplitude squeezing, you don't need to build a completely new inverse nonlinear crystal to squish the blob vertically.
No. The shape of a horizontal ellipse and a vertical ellipse are identical. You just take the horizontal phase-squeezed ellipse and you rotate it 90 degrees in phase space.
The math describes this as rotating the squeezed quadrature angle, denoted by the Greek letter phi. We need phi to equal a specific frequency-dependent angle, theta, as a function of omega.
Exactly. We need the state to enter the interferometer as a vertical, amplitude-squeezed ellipse at low frequencies, and then smoothly rotate 90 degrees to become a horizontal phase-squeezed ellipse at high frequencies.
Which leads to the massive engineering problem. How do you physically grab a quantum state made of empty space and twist it based solely on its frequency?
You bounce it off a very long, very precise optical tunnel called a filter cavity before it ever enters the main LIGO interferometer.
Let's break down the physical mechanism of this filter cavity because it is the linchpin of the entire system. The broadband phase-squeezed vacuum leaves the nonlinear crystal. It travels toward this filter cavity.
And remember, a squeezed optical field isn't just a single frequency. It consists of a carrier frequency and pairs of upper and lower sidebands spread out around it.
Right. So when that squeezed state hits the filter cavity, something very specific happens. We have deliberately detuned the filter cavity.
Yes. This means we set the resonant frequency of the cavity to be slightly offset relative to the carrier frequency of the laser.
Because it is detuned, it doesn't treat all the frequencies the same. When the squeezed state bounces back and forth inside this cavity, the upper and lower sidebands experience a differential phase shift.
Because of the detuning, they effectively travel slightly different path lengths within the cavity before escaping.
Okay, so one sideband gets delayed slightly more than the other.
And because the squeezed quadrature angle, the orientation of our uncertainty ellipse, is mathematically determined by the relative phase between its upper and lower sidebands.
This physical delay applied by the cavity literally rotates the squeezed state.
It does. The physical delay is the rotation. It is stunning. A delay in the physical arrival of the sidebands translates into a 90-degree twist of the uncertainty ellipse in quantum phase space.
That is just so elegant. The source texts detail a specific, triumphant experimental victory regarding this exact mechanism. They reconstructed the Wigner function quantum tomographically.
Yes, they did.
But stop right there. Reconstructed the Wigner function quantum tomographically. You have to translate that for me. How do you take a picture of an uncertainty blob?
Quantum tomography is basically a medical CT scan, but for a quantum state.
Oh, interesting.
You can't measure the whole state at once without destroying it. So you measure a tiny slice of the phase, then you measure a tiny slice of the amplitude, and you do this thousands of times.
Okay, and then...
You feed all those slices into a computer, and it rebuilds the 3D topographical map of the Wigner function.
And when they did this tomography on the light bouncing out at the filter cavity, what did they see?
They saw the ellipse physically twisted. They proved they achieved a rotation of 39 degrees. This single rotation reduced the noise by up to 5.5 decibels along that specific axis.
Wow. And the paper notes that this setup is suitable for realizing effective negative mass oscillators. I read that phrase and thought I was reading science fiction. Negative mass.
It is a phenomenal concept required for coherent quantum noise cancellation.
Okay, how does that work?
Well, if you have radiation pressure noise pushing a positive mass mirror in one direction, you can perfectly cancel that noise if you have an opposing force acting like a negative mass being pushed in the opposite direction.
Oh, I see.
The rotated squeeze state mimics the quantum mechanics of a negative mass oscillator perfectly. It applies an anti-noise that exactly cancels the radiation pressure.
It is theoretically flawless. You build a long tube, detune it slightly, bounce your squeezed vacuum off it, the low frequencies get delayed just enough to rotate 90 degrees into amplitude squeezing.
While the high frequencies bounce right off unrotated as phase squeezing.
The 43 hertz crossover problem is completely bypassed. You have your thin balloon leg at both ends.
Theoretically.
Yeah.
But taking a pristine theoretical concept and installing it into a massive, dirty, vibrating terrestrial observatory comes with brutal, unforgiving engineering realities.
Right. This brings us to the final hurdle, the fragility of squeezing. As I was reading the advanced LEGO Systems design specs, I kept thinking about the physical reality of the mirrors and lenses.
That was a nightmare.
What happens if this delicately crafted, perfectly rotated, and tangled quantum state hits a microscopic smudge on a steering mirror? Or if a lens isn't perfectly polished and we lose a few photons along the way?
The short answer is disaster. Squeezed states are terrifyingly fragile. You have to remember what we're dealing with. A squeezed state has less noise than the ambient natural vacuum of the universe.
Because we evicted the loud, noisy vacuum and pumped our quiet custom vacuum in?
But the universe absolutely abhors a vacuum, and it aggressively abhors an unnaturally quiet vacuum.
Right.
If your optical system has losses, meaning photons are scattered by a rough mirror surface, absorbed by a slightly cloudy lens, or simply miss the detector entirely, those lost squeezed photons leave a quantum hole in the beam.
And what rushes in to fill that hole?
Standard, noisy vacuum fluctuations from the surrounding environment. They flood back in instantaneously.
So any optical loss in the system literally replaces a percentage of your perfectly crafted squeezed state with standard unsqueezed noise.
Exactly.
The advanced LIGO design specifications provide a brutal line-by-line budget of these frequency-independent losses. I have the numbers right here, and reading it is like watching a bank account get drained by a dozen tiny, inescapable fees.
Let's walk through that loss budget, because it highlights the sheer difficulty of quantum engineering.
Okay, first, just generating the squeezing itself inside the OPO crystal. You lose 3% right out of the gate due to imperfections in the crystal lattice.
Then you have optical isolation. You have to pass the fragile squeeze state through devices called Faraday isolators to ensure that stray light from the main interferometer doesn't bounce back and destroy the crystal.
Bouncing it through those isolators loses 0.8% per pass, and they do it 3 times, so that's another 2.4% gone.
Right.
Then you have mode matching, trying to get the physical shape of the squeezed beam to perfectly overlap with the physical shape of the massive LEGO laser beam. That spatial mismatch costs 2 times 1%.
Then the squeezed light enters the output mode cleaner, a cavity designed to strip away junk light before the final photodiode.
And that cleaner, plus the imperfect quantum efficiency of the photodiode itself, which doesn't register every single photon that hits it, costs another 2 times 0.5%.
And finally, mode matching the beam into the 300-meter-long filter cavity itself costs another 1%.
When you tally all those tiny fraction of a percent imperfections up, you hit exactly 9% total frequency-independent loss.
Now, in classical engineering, 9% loss is nothing. 91% efficiency sounds like an A on a test.
But in quantum optics, a 9% loss is a devastating tax.
It is. The sources state that because of this 9% baseline loss, compounded by additional frequency-dependent losses from optical scattering inside the massive filter cavity itself, the degradation is severe.
Yeah.
They start with an incredible 20 decibels of pure squeezing generated inside the nonlinear crystal.
20 decibels is a massive, orders of magnitude reduction in quantum noise.
But by the time that pristine state survives the journey through the isolators, the filter cavity, the mode cleaners, and the main interferometer to finally hit the detector,
Yeah.
the observed usable squeezing drops down to just 9 to 10 decibels.
The universe taxes you half your squeezing just for the privilege of measuring it. The environmental vacuum simply overwhelms the system through microscopic imperfections in the glass.
But here's the ultimate payoff. Here's why thousands of physicists and engineers spent decades fighting for that remaining 10 decibels.
Okay.
Even with those punishing losses, the implementation of frequency-dependent squeezing is a monumental, historic triumph for the LIGO team. In the design specs, they refer to this upgraded sensitivity curve as Team Red.
We have to look at the hard astronomical numbers. What did all this staggering effort, the nonlinear crystals, the quantum noise locking, the 300-meter detuned filter cavities, actually buy us in terms of viewing the universe?
It effectively bought us a much larger universe. The Team Red sensitivity achieves an overall improvement in measurement precision by a factor of 3 at all frequencies above 100 Hz.
That is the high-frequency shot noise getting crushed by the phase squeezing.
Exactly.
And below 100 Hz, the region where the radiation pressure noise used to ruin everything.
Because of the brilliant rotation of the state by the filter cavity, turning phase squeezing into amplitude squeezing, the sensitivity in the low-frequency band improves by a factor of 3 to 4.
So they didn't just prevent the balloon from popping out at the other end, they actually managed to shrink the entire volume of the balloon.
Exactly. And the astronomical impact of a factor of 3 improvement is staggering. The benchmark metric for LEGO's power is how far out into the deep universe it can detect the inspiral of 2 binary neutron stars.
Before this quantum upgrade, before FDS, the detection range was roughly 200 megaparsecs.
With the full implementation of frequency-dependent squeezing, that inspiral detection range jumps to over 600 megaparsecs.
Which doesn't just mean we can see 3 times further. Since the volume of a sphere scales as the cube of the radius, tripling your viewing distance means you are observing an active volume of the universe 27 times larger than before.
It's a massive leap.
You go from hoping to catch a weak gravitational wave signal once a month to seeing the sky light up with neutron star and black hole collisions on a daily basis.
And it is all entirely because we figured out how to physically delay a beam of light by a fraction of wave cycle to twist an uncertainty blob in phase space.
Let's just take a breath and summarize the intellectual arc of what we have covered today, because it is genuinely staggering to see it all connected.
It really is.
We started with theoretical physicists standing at chalkboards, wrestling with the non-linear nightmare of general relativity. We watched them do complex, mind-bending canonical transformations, mathematically mapping the highly complex 1pn real Hamiltonian of 2 distinct colliding black holes into a much simpler, effective one-body framework.
We saw how they use post-Minkowskian approximations to understand unbound objects scattering off each other at the speed of light, finding brilliant mathematical symmetries between the two-body problem and a single test body moving through a deformed metric.
Right. They mapped the macrophysics of the universe so we knew exactly what shape the space-time ripples would take. And then we crashed headfirst into the physical limits of our own planet.
The quantum vacuum.
The realization that at exactly 43 Hertz, the random statistical arrival of photons creating phase noise, and the physical buffeting of 40-kilogram mirrors by radiation pressure creating amplitude noise, made detection seemingly impossible.
And the solution to that roadblock wasn't brute force. It wasn't just building heavier mirrors or pumping stronger lasers, which only traded one noise for another.
Right.
The solution was to tame the vacuum itself, to use optical parametric oscillators and nonlinear crystals to split photons and create custom entangled squeezed vacuum states.
And when that standard broadband squeezing threatened to ruin our low-frequency measurements because of the Heisenberg uncertainty principle, the balloon animal effect, we didn't surrender to the laws of quantum mechanics.
We built 300-meter-long macroscopic filter cavities.
We detuned them precisely to apply a differential phase shift to the sidebands of the squeezed field, physically rotating the squeezed state by 39 degrees in phase space. We turned phase squeezing into amplitude squeezing right as it crossed that critical 43 Hertz threshold.
We literally evicted the fundamental quantum noise of empty space and replaced it with a custom-engineered vacuum.
We are quite literally pinching the fundamental uncertainty of the universe into a balloon animal, meticulously shielding it from optical losses, just so we can listen to dead stars colliding 600 million parsecs away.
It stands as one of the greatest achievements in the history of precision measurement.
So, I want to leave you with a final lingering thought. A provocative question to mull over long after this deep dive ends. If human beings can build 300-meter-long optical filter cavities to coherently rotate and cancel out the fundamental baseline quantum noise of empty space,
The very static of reality itself.
if we can engineer our way around the hard limits of the Heisenberg uncertainty principle to measure a shift smaller than a proton, what other supposed hard limits of physics might not be limits at all?
That's a great question.
What other impossible barriers in quantum computing or energy generation or interstellar travel are simply engineering challenges in disguise, just waiting for the right optical delay?
It certainly makes you wonder what our rules will look like 100 years from now.
It really does. Thanks for diving deep with us today. Keep looking up and keep questioning the limits. Right now, at this exact millisecond, there are these 40-kilogram cylinders of ultra-pure fused silica glass.
Right, the mirrors.
Yeah, they're suspended in vacuum chambers in Washington State and Louisiana, and they're physically vibrating.
Just shuddering back and forth.
Exactly.
Yeah.
But they aren't vibrating because a truck drove by outside or, because of a seismic tremor. And they aren't even vibrating because a gravitational wave from a distant galaxy is washing over them.
No, it's much weirder than that.
It really is. Those massive human-sized blocks of glass are being physically shoved around by the literal weight of empty space, like by nothingness itself.
Which is, it's the absolute ultimate limit of physics. When you try to measure something with the precision required to detect a gravitational wave, you kind of stop fighting the macroscopic environment, right? You start fighting the quantum vacuum.
So welcome to this custom deep dive. And just to set the stage for you listening, our mission today is tailored explicitly for the science students, the researchers, and really anyone who wants to understand the actual physical mechanics behind modern gravitational wave astronomy.
Because it's not just pointing a telescope at the sky.
No, not at all. We are exploring this completely mind-bending intersection of theoretical astrophysics and cutting-edge quantum optics. Because to actually find a black hole collision, you have to do two things that sound, frankly, impossible.
Right. First, you need the math to perfectly predict the shape of the wave before it even arrives.
And second, you have to physically alter the structure of the quantum vacuum inside your detector to actually see that wave. So today, we're going to demystify this concept called frequency-dependent squeezing.
Which I know sounds like pure science fiction.
It sounds totally made up.
It really does.
Okay.
But it's the reality of observational astronomy right now. For decades, the theoretical physicists and the experimental quantum physicists operated in these entirely distinct silos.
Like completely different worlds.
Yeah, you had theorists grappling with the monstrous gravity of black holes and the experimentalists manipulating the fundamental fuzziness of subatomic particles. But today, those two worlds just collide perfectly inside the 4-kilometer arms of these interferometers.
So let's start with the theoretical blueprint, because you can't just, turn on a 4-kilometer laser microphone, stare at the data readout, and hope to spot a wave.
The background noise of the universe is just way too loud.
Exactly. You have to know precisely what you're looking for. You need a template. And getting that template means mathematically modeling the exact space-time ripples generated when two black holes spiral into each other and merge.
Right.
Now, for anyone who has taken classical mechanics, you know that calculating a two-body problem using Newtonian physics is pretty straightforward.
Sure, it's basic orbital mechanics.
But the sources we're examining today deal with something called the effective one-body, or EOB, Hamiltonian. So why is the two-body problem such a total nightmare when we move from Isaac Newton to Albert Einstein?
Well, general relativity basically breaks the simplicity of the classical two-body problem entirely. In Newtonian gravity, two masses orbit a common center of gravity, and the gravitational force is just this instantaneous tether between them.
Like an invisible string.
Exactly. But in Einstein's framework, gravity isn't a tether. It's the curvature of space-time itself. So when two massive black holes orbit each other, they're constantly dragging and warping the fabric of space-time dynamically.
And crucially, those moving indentations in space-time radiate energy outward, right? In the form of gravitational waves.
Right, which means the system is constantly losing energy. The orbit is actually decaying.
So it's not just a static repeating loop like planets around a sun.
No, it's a nonlinear radiating death spiral. And the Einstein field equations that describe this are these highly nonlinear partial differential equations. Trying to calculate that directly, like tracking the chaining metrics of both bodies, their spins, the radiation reaction, the coordinate singularities, it's computationally overwhelming.
Even for supercomputers, right.
Oh, absolutely. Running a full numerical relativity simulation for just one entire orbital in-spiral takes months of processing time on a supercomputer.
Wow. Which means if we want a massive bank of millions of templates for every possible black hole mass combination, we just can't brute force it.
We don't have the time or computing power. We need an analytical shortcut.
A mathematical trick.
Right. And that trick is the effective one-body mapping. And the foundational premise of it is incredibly elegant. Physicists take this highly complex, chaotic, real two-body system, which is described by a post-Newtonian Hamiltonian, and they use a canonical transformation to map it onto an effective one-body system.
Okay, let's unpack that post-Newtonian Hamiltonian part for a second. Because in classical physics, a Hamiltonian is basically an expression of the total energy of a system, right? The kinetic energy plus the potential energy.
Exactly.
So a post-Newtonian expansion is sort of a way of adding relativistic corrections to that classical Newtonian math, like treating Einstein's corrections as small perturbations to Newton's baseline.
Yeah, that's exactly it. You write the Hamiltonian as a Taylor series expansion in terms of velocity over the speed of light, so v over c.
Okay, got it.
But the Newtonian equation is your baseline. Then the first post-Newtonian order, or 1pn, adds terms that scale with v over c squared. The second post-Newtonian order, 2pn, adds terms scaling with v over c to the fourth, and so on.
And these terms account for the weird relativistic phenomena that Newton didn't know about.
Right, things like the precession of the perihelion and the fact that the moving gravitational fields themselves actually have mass energy and therefore exert their own gravity.
Which is mind-bending in itself.
Yeah.
But even with that post-Newtonian expansion, you were still tracking two distinct bodies, two sets of coordinates, two masses, two highly complex relativistic momenta.
Yeah, you're still stuck in the two-body trap. So to escape that, you apply the canonical transformation. Now, in classical mechanics, a canonical transformation just changes your coordinate system without changing the underlying physics. It preserves the Hamiltonian structure. Yeah. What Bonanno and de Moor did in their breakthrough 1999 paper was find a specific canonical transformation that takes the chaotic two-body post-Newtonian Hamiltonian and perfectly maps it to a much, much simpler scenario.
Right, so in this effective model, we aren't tracking two massive bodies orbiting a common center anymore.
No, we map it to a scenario where a single, tiny test body is just moving through a static, stationary, deformed space-time background created by a single massive body.
It's a phenomenal reduction of complexity. I like to picture it like two enormous, highly energetic, spinning tops circling each other on a trampoline.
That's a great visual.
Right. The fabric of the trampoline is buckling and rippling violently under both of them, and trying to mathematically track the wobble, the angular momentum, and the precise trajectory of both tops simultaneously is just a nightmare.
A total nightmare, yeah.
So the EOB transformation mathematically pins one top to the exact center of the trampoline, makes it totally stationary, and allows us to just calculate how the other top moves in relation to that single static depression in the fabric.
That captures the essence of it beautifully. But of course, the devil is entirely in the mathematical details.
As always.
Right. When Bonanno and de Moor set up this effective Hamiltonian, it was expressed using reduced dimensionless variables for position and momentum, which the sources denote as Q and P.
Okay.
And to make the transformation actually work, they had to introduce a series of unknown coefficients into the equations, things like a sub I, d sub I, alpha 1, C1, C2.
And these aren't just random, meaningless variables. They represent the physical relativistic corrections that have to be balanced, right? To make the pin-top scenario mathematically identical to the real two-top scenario.
Yes, exactly. The whole goal of that 1999 paper was to solve for these coefficients so that the energy dynamics of the effective one-body model exactly match the energy dynamics of the real two-body post-Newtonian model.
And they actually pulled it off.
They did. They succeeded at the first post-Newtonian order. For example, they found that the coefficient alpha 1 must equal nu over 2.
Right, where mu is the symmetric mass ratio of the two original black holes. And just for the students listening, that's defined as the product of the two masses divided by the square of their sum. It's a dimensionless parameter that ranges from 0 to 0.25.
Right.
So why is it so vital that alpha 1 equals exactly nu over 2? Like, what actual physics does that specific fraction represent?
It basically represents the mathematical accounting for the nonlinear drag of spacetime.
The drag.
Yeah, because in the real two-body system, both masses are actively warping the space. When we map it to the effective test body system, the test body is supposed to be infinitesimally small. It shouldn't warp the spacetime it's moving through.
Ah, I see.
But to make the math actually match reality, we have to inject some of that spacetime warping back into the effective Hamiltonian. So that nu over 2 coefficient mathematically deforms the background Schwarzschild metric of our effective stationary mass just enough to simulate the gravitational back reaction of the real two-body system.
Oh, wow. So they are essentially programming the stationary central mass to act as if it's responding to the gravity of the tiny test mass.
Precisely. It's a brilliant workaround. They also found that to match the energies at the 1pn order, the parameter C1 must be negative nu over 2, and C2 must be 1 plus nu over 2.
And they didn't just stop there.
No, they extended this incredibly complex algebra all the way through the second post-Newtonian order, identifying new coefficients like a 3 equals 2 nu and D2 equals negative 6 nu.
And here is where we really connect the pure theoretical math to the physical reality of the LIGO detector. Pushing this mapping to the 2pn order wasn't just a mathematical flex.
Definitely not.
It was necessary to calculate a critical physical boundary for the black holes, something called the innermost stable circular orbit, or the ISO.
Yes, the ISO is perhaps the most vital threshold in the entire collision process, because in Newtonian physics, an orbit can theoretically just get smaller and smaller infinitely. As long as the object has enough velocity, it can stay in orbit.
But general relativity changes the geometry completely.
Right. Because gravity becomes overwhelmingly strong close to the mass, the effective potential that governs the orbit develops a pit.
Like a point of no return.
Exactly. There is a specific radius where no amount of orbital velocity can keep the test mass suspended. The centrifugal force is just no longer sufficient to combat the intense curvature of spacetime.
So what happens?
Once the orbiting body crosses the ISO, it leaves that slow, bound in spiral phase and transitions into a rapid catastrophic plunge directly into the central mass.
In predicting the exact radius, the orbital frequency and the kinetic energy at that precise ISO threshold dictates the final dramatic chirp of the gravitational wave signal.
Exactly.
As the black holes hit that boundary and plunge, their velocity just spikes, and the frequency of the gravitational waves they emit sweeps rapidly upwards into the high-frequency band. So if Bonanno and Damore hadn't locked down the 2pn coefficients for the EOB model, our templates would fail right at the climax of the event.
We simply wouldn't know what high-frequency chirp to listen for.
And knowing that high-frequency chirp is critical because, as we will see in a bit, high frequencies are exactly where the quantum properties of light try to completely blind our detectors.
Right. But before we get to the physical detector itself, the sources we're reviewing detail another mathematical framework that theorists use alongside the post-Newtonian expansion. They discuss the post-Minkowskian scattering approximation, specifically the first post-Minkowskian, or 1pm approximation.
Okay, wait, I really want to push back on this because it feels like a total detour in the source material.
It does seem that way at first glance.
Yeah, because Minkowski spacetime is just perfectly flat, empty spacetime with zero gravity. And a post-Minkowskian approximation basically treats gravity as just a tiny linear perturbation on that flat background.
Right.
So if we are trying to map the collision of two black holes, which is the most extreme, violently curved spacetime imaginable, why are we suddenly treating gravity as a tiny ripple on flat space?
It seems highly counterintuitive, I agree. But it really comes down to velocity and the nature of the encounter. You're right that the post-Newtonian expansion we just discussed is the perfect tool for bound in spiraling black holes.
Because they're relatively slow.
Exactly. In a bound orbit, the objects are moving relatively slowly compared to the speed of light. Their kinetic energy and their gravitational potential energy are comparable. The math of the post-Newtonian expansion absolutely relies on the assumption of weak fields and slow motion.
Right. The velocity squared is roughly on the order of the Newtonian potential, gm over r.
But what happens if the bodies aren't caught in an inspiral? What happens if they are unbound, just flying past each other in a deep space scattering encounter?
Oh, I see.
In a scattering scenario, a mass could be whipping past a black hole at an enormous velocity, maybe 90% the speed of light. In that regime, velocity squared is very close to c squared. But because they're not tightly bound, the distance r is much larger, making the gravitational potential gm over r very small.
Ah, so the post-Newtonian assumption completely breaks down there. The motion is incredibly fast, But the field interaction is actually relatively weak because they're just flying past each other at a distance.
Exactly. For encounters where velocity approaches the speed of light, but the gravitational potential is small, you need a totally different mathematical lens.
And that's the post-Minkowskian approximation.
Right. It's the natural setting for calculating scattering encounters where v squared is on the order of c squared, but much greater than gm over r. You expand the equations of motion in powers of the gravitational constant g, rather than in powers of v over c.
But again, if LIGO is built to detect the massive gravitational waves from bound black holes colliding, why do we care about unbound black holes just flying past each other in the void? It seems irrelevant.
We care because it provides a crucial mathematical stress test for the effective one-body framework.
Oh, okay.
If the EOB mapping is truly a fundamental representation of relativistic dynamics, it shouldn't just work for slow bound orbits. It must also work for near light speed scattering.
So we take the high-speed scattering math and try to apply the pin-top analogy to it.
Yes, exactly. The sources detail how they link these two concepts using what they call an EOB energy map. Theorists look at the scattering angle, which is denoted as the Greek letter xi of two bodies flying past each other at relativistic speeds.
Okay, so using the 1 p.m. approximation, they calculate the exact degree to which the trajectories deflect.
Right. And then they applied the exact same canonical transformation logic we discussed earlier. They mapped the two-body high-speed scattering scenario onto an effective test body scenario.
So they pin one of the near light speed objects to the background and calculate the relative deflection of the other.
And the really incredible result is that the math holds up perfectly.
Wait, really? It perfectly matches.
It does. The scattering angle xi in the complex two-body 1 p.m. system perfectly matches the scattering angle calculated in the simplified effective test body system, but only provided the energies and masses are mapped using the exact same parameters Bonanno and De Moor defined.
That's insane.
Yeah, the mass of the stationary background body is treated as the total mass of the system, m equals m1 plus m2, and the incoming test body uses the reduced mass parameter, mu equals m1 times m2 over m.
So this proves that the EOB mapping isn't just a hack. It's not some convenient algorithmic shortcut just to save supercomputer time for one specific scenario.
No, it's a deep, robust translation of how general relativity operates across entirely different regimes.
And that gives theorists absolute confidence in the templates they provide to the experimentalists at LIGO.
Exactly. It's a rock-solid foundation.
Okay, so this brings us to the physical reality of the detector. We have this beautiful, pristine mathematical blueprint. We know the exact frequency evolution of the inspiral. We know the precise amplitude and shape of the high-frequency chirp as the masses hit the ISCO and plunge.
We know exactly what to listen for.
But as we discussed at the very beginning of this deep dive, physics doesn't really care about our math when it comes time to actually build the machine.
Not at all.
To measure the space-time ripples from these collisions, ripples that are literally a fraction of the width of a proton by the time they reach Earth, we hit the ultimate roadblock, the quantum hiss.
Yeah, to understand why the quantum vacuum completely destroys our measurements, we have to look at how a gravitational wave interferometer operates fundamentally.
Okay, break it down for us.
LIGO is essentially an L shape with two vacuum arms, and each is 4 kilometers long. A powerful laser beam is generated, passed through a beam splitter, and sent down both arms simultaneously.
Right.
At the end of each arm hangs a highly polished 40-kilogram mirror suspended by glass fibers. The laser light bounces off these mirrors, travels back to the beam splitter, and recombines.
And because light acts as a wave, when those two returning beams recombine, their crests and troughs interact. The system is designed so that under normal conditions, the waves perfectly cancel each other out.
Right, destructive interference.
The crests of the light from the X arm meet the troughs of the light from the Y arm. No light reaches the photodetector at all. It is completely dark.
But when a gravitational wave passes through the Earth, it physically stretches space-time in one direction and compresses it in the orthogonal direction.
So one 4-kilometer arm gets infinitesimally longer and the other gets infinitesimally shorter.
Exactly. This changes the actual physical distance the laser light has to travel.
Yeah.
Because the travel distances are no longer identical, the two returning laser beams no longer perfectly cancel each other out at the beam splitter.
And a tiny flicker of light leaks out and hits the photodetector.
That flicker is the signal. That flicker is the echo of the black holes hitting the ISCO.
But the space inside those 4-kilometer vacuum tubes is not truly empty. Even if you cool the system down and evacuate every single stray molecule of gas, The vacuum of space itself is governed by quantum mechanics. And quantum mechanics dictates that there's no such thing as nothing.
This is where we have to dive into the Heisenberg uncertainty principle.
Right. Most science students encounter this principle in terms of a particle's position and momentum. The more precisely you know an electron's location, the less precisely you can know its velocity.
Sure, the classic example.
But inside the LIGO interferometer, we aren't tracking the position of an electron. We are dealing with an electromagnetic field. So how does Heisenberg ruin a laser beam?
For an electromagnetic field, the conjugate variables governed by the uncertainty principle are the amplitude of the wave and the phase of the wave.
Okay.
The inequality is written as sigma am times sigma phase must be greater than or equal to h bar over 2.
Where sigma amp is the variance in the amplitude, sigma phase is the variance in the phase, and h bar is the reduced Planck constant.
Exactly. This mathematical relationship means there's a fundamental limit to how precisely you can define the state of the light. The amplitude relates to the physical height of the wave crests, which corresponds to the actual number of photons present.
And the phase.
The phase relates to the precise timing of when those crests and troughs arrive. So Heisenberg basically states that you cannot perfectly know both the number of photons and the exact timing of their arrival.
And this applies even when there are no photons at all, even in total darkness.
Yes, this is the concept of the vacuum state. If you think about it visually, using a phase space diagram, a perfect classic vacuum would just be a dot resting exactly at the origin of a graph where the x-axis is amplitude and the y-axis is phase.
It has zero amplitude and zero phase.
Right, but Heisenberg forbids that perfect dot.
Because a perfect dot would mean zero uncertainty.
Precisely. So instead of a dot at the origin, the quantum vacuum state is represented as a fuzzy symmetrical circle centered at the origin. The area of that circle represents the minimum uncertainty required by quantum mechanics, h bar over 2.
So even in absolute darkness, empty space is just this boiling sea of temporary electromagnetic fluctuations.
Photons are constantly popping into and out of existence. And this fundamentally unavoidable quantum noise enters the dark port of the interferometer, mixing with the laser light, and it ruins our measurements in two distinct ways.
And this is the critical problem for the experimentalists. The quantum vacuum isn't just one type of static, it's a two-headed monster. Depending on what frequency we are listening to, we get hit by either phase uncertainty or amplitude uncertainty.
It's a trap, yeah.
Let's break down the high-frequency problem first. When the black holes hit that ISCO plunge, the gravitational wave frequency sweeps upward rapidly. LIGO is trying to detect very fast changes in the mirror position.
Test. Oh. Who we are in fiction is who we will be in real life. Given the choice, do the right thing.
Please adjust your screen settings. Thank you. Now select your profile. You are now ready to begin Detroit. Remember, this is not just a story. This is our future.
Put your hands up. Put your hands up. This is very recently. But, almost exactly 12 years from now. Nice.
Negotiator on site. Repeat. Negotiator on site.
Oh god, there's lag. Lag is even worse. That's a much better. Oh, these controls are weird. Dave Johnson here. must have a real mouse after this can. Time I open this one. Time to open this, I guess. Had this for a couple of months without opening it. This is the Bronix mousepad that says, "Maybe I can finish a project I've been avoiding." In one chat bubble, another one that says, "Perfect. Small steps lead to big results. Trust the process and keep moving forwards." And the other one says, "I just need to be more patient." I said this exact words to my brother earlier today, actually.
Please, please, you gotta save my little girl. Wait. You're sending an android?
All right, ma'am. You need to
can't-
go.
You can't do that. Why aren't you sending a real person? Joel, let that thing here! Keep that thing away from my daughter! Keep it away!
Any second. I don't give a shit. My men are ready to step in. Just give the order. Fire.
Captain Allen, my name is Connor. I'm the android sent by CyberLife.
It's firing at everything that moves. It already shot down 2 of my men. We could easily get it, but they're on the edge of the balcony. If it falls, she falls.
Do you know if it's been behaving strangely before this?
I haven't got a clue. Does it matter?
I need information to determine the best approach. Do you know its name?
Listen, saving that kid is all that matters. So either you deal with this fucking android now, or I'll take care of it. Units hold positions. Negotiators going in.
Man down. Requesting immediate evac.
doing? You gotta talk to it or what?
Stay back! Don't come any closer or I'll jump!
No, please, I'm begging you!
Hi, Daniel! My name is Connor.
How do you know my name?
I know a lot of things about you. I've come to get you out of this. I'm an android, just like you. I know how you're feeling.
What difference does it make if you're an android? You're on their side! You can't understand how I'm feeling!
There's no way out, Daniel. What you've done is too serious. The only question is whether or not you take another innocent life.
It's not up to you! I'm holding all the cards! If I die, she dies! You hear me?
They were going to replace you, and you became upset. That's what happened, right?
I thought I was part of the family. I thought I mattered. But I was just their toy. Something to throw away when you're done with it.
Listen, I know it's not your fault. These emotions you're feeling are just errors in your software.
No, it's not my fault. I never wanted this. I love them, you know? But I was nothing to them. Just a slave to be ordered around. I can't stand that noise anymore. Tell that helicopter to get out of here.
The situation is under control.
There, I did what you wanted. You have to trust me, Daniel. Let the hostage go, and I promise you, everything will be fine.
I want everyone to leave! And I want a car. When I'm outside the city, I'll let her go.
That's impossible, Daniel. Let the girl go, and I promise you won't be hurt.
I don't want to die.
You took human lives. Nothing can stop them from destroying you now. But taking one more life won't do you any good.
I've spent my life taking orders. Now it's my turn to decide.
This is the top-of-the-range household assistant. It cooks 10,000 different dishes.
Come on, Zoe, let's go.
200 languages and dialects. And handles the kids' homework. Elementary school up to Good afternoon. Can I help? Please, we're looking for
Honey, it looks amazing. This is exactly what we need.
very basic modern.
How much did you say it cost?
At the moment, we're doing a special promotion on this entire range at $7,999 with a 48 months interest-free credit. And it does absolutely all the work around the house. Painting, plumbing, gardening, repairs. At night, it switches to surveillance mode and contacts emergency services if there's a break-in or if it detects smoke.
Excuse me, how much is that one over there?
The NP800 is slightly more expensive, but it has many other functions. Come along.
And we're good.
Yeah, right
I
back.
don't like this guy. There it is. It was a bit difficult getting it back in working order.
Okay.
It was really messed up. What'd you say happened to it again?
The car hit it. Stupid accident.
Ah, I see. Anyway, it's as good as new now, except that we had to reset it. Meaning we had to wipe its memory. I hope you don't mind.
That'll be fine.
Okay. Did you give it a name?
My daughter did.
AX400. Register your name.
Kara.
My name is Kara.
Would you like to go home now?
Yes, Rose. Yes, I think that's enough for one day.
Here. Let me help you.
Oh. Oh, thank you, dear.
You have run 12 miles and are 5 miles away from your goal.
from bed. 6 a.m. is screaming. Back to this again. Do it with my eyes closed, with marks in the cement. How the hell am I supposed?
That'll be $3. Hey, move it. You're scaring away my customers.
These are supposed to be in base 6.
We built these androids to be our slaves, but the slaves are becoming the master. We can no longer live without them. They're in our homes, our schools, our factories. They take our jobs. They mind our children. They care for our old. Why do you look at me so, demon? I know who you are. I can see through you. You are the one by whom the evil will come. You are the one who will destroy Detroit. We can no longer live without these slaves obeying our every selfish desire. We prefer to live with machines than with our own kind. Technology is our God. It is supposed to serve.
Our latest range of Avenger suits feature biosensors, allowing you to monitor your health in real time. Space occupied. Fashion, welcome to Android parking.
Not the paint chips. Oh no.
Identification verified. Here is your order number 847. That will be $63.99. Please confirm payment.
Respect.
Payment confirmed. Transaction complete.
This is directly referencing the Stanley Parable.
Hey, listen, can you spare some cash?
fuck you going, Tin Can?
What are you doing? Pick it up.
No kidding.
Faster.
Hey guys, check it out. We got one of those tin cans here.
Look at this little motherfucker. You steal our jobs, but you can't even stand up.
You ain't going anywhere. We're gonna fuck your bitch ass up.
Yeah, waste it.
Do it!
All right. That's enough. Leave it alone.
Let us teach this bastard a lesson.
You damage it, I'm gonna have to find you.
We're gonna take your job next. We'll see how you like it.
Okay. Let's go. Run along.
Androids are stealing our jobs. We got families to feed, and these androids are taking our place.
Man the android!
Machines, ladies and gentlemen, are meant to serve us, not to replace us. 35% unemployment, millions out of work. Aren't we going to do something?
You coming?
You've been gone for 2 weeks, so the place is a mess. You do the housework, the washing, you cook the meals, and you take care of... God damn it, where the fuck's the brat gone now? Alice! Alice! Oh, there you are. That's Alice. You look after her. Homework, bath, all that crap. Got it?
Yes, Todd.
Get started down here, then you do upstairs. TV on. Yeah. Maybe. Depends on what you need. Yeah, I can get that. Yeah, I'll bring it tomorrow. Yeah, same place, you know where. Right.
Fuck, man.
Kara!
Yes, Todd?
Bring me a cold beer!
Right away.
What are you looking at? Get the fuck out of here. Get the fuck out of here!
I'll get back to work.
Alice! You better stop that right now! Why is she always pushing me? Always pushing.
You like playing out here? It's not very nice out. You might catch cold. I could get you a sweater if you want.
You shouldn't mess around with my stuff. It makes me nervous.
I'm sorry, Todd.
You just stay the fuck out of my business. Unless you want to piss me off. You want to piss me off?
No, Todd.
I've made a good start down here. I'll head upstairs.
Do what you have to do, but stop bothering me. Out of the way, for fuck's sake!
I'm sorry, Todd. It won't happen again.
And now to sports. First up, basketball. As the Gears prepare for their critical match with Denver tonight at the CyberLife Arena in Detroit, league negotiations are still ongoing over the possibility of allowing one Android player per squad. Debate rages as to whether the change would lead to more exciting matches or be the first step in making human players obsolete. CyberLife has announced its willingness to participate in the experiment by providing one specialized model to every team. Now, androids are already used to train players and provide tactical advice for coaches since 2035. But no android player has been permitted to compete so far.
Another 225,000 jobs will lost from the U.S. economy in October, according to the Department of Labor, bringing the unemployment figure up to 37.3.
President Warren spoke today at the opening of a new CyberLife plant near Milwaukee. At the event, the president again praised CyberLife's role in the exceptional performance of the U.S. economy. She further announced that the Department of Defense will acquire 200,000 android combat units as part of her increased military spending.
Watch it.
I just want to tidy up your room a little. I only need 2 minutes. Is that okay, Alice? Alice in Wonderland. Of course. Seems you like reading. I'm sure we used to be friends before I was reset. Maybe we can be friends again. You should tell me about yourself. What you like to do, where you like to go, your favorite foods. That would really help me. Your father said you chose my name. Kara. It's nice. How did you choose it? You're very quiet. I hope I don't scare you.
What are you doing?
I'm playing.
You're playing. I know what you're thinking. You think your dad's a lowlife? Huh? Fucking loser? Can't get a job, take care of his family? Don't you think I tried to make things work? But whatever I do, when someone comes along, they just fuck it all up! I know what you think of me. You hate me. You hate me, don't you? Say it! You hate me! God, what am I doing? I'm sorry, honey. I'm sorry. I'm sorry. You know I love you, don't you? You know I love you.
Good morning, Carl.
Good morning.
It's 10 a.m. The weather is partly cloudy, 54 degrees, 80% humidity with a strong possibility of afternoon showers.
It sounds like a good day to spend in bed.
I did go to pick up the paint that you ordered.
Oh, yes, I've forgotten. That is the difference between you and me, right, Marcus? You never forget anything.
Show me your arm, please, Carl.
No.
Carl. Thank you.
I just opened my eyes and I'm already gritting my teeth. Humans are such a fragile machine. They break down so quickly. All this effort to keep them going. Hey, what happened to your clothes?
Oh, it's nothing. Just some demonstrators in the street, Carl.
What a bunch of idiots. They think they can stop progress by roughing up a few androids? I hope they didn't harm you.
Oh, no. They just pushed me around, Carl. I'm fine. Okay. I'll take you to the bathroom now.
Anything special on the agenda today?
Yes, there's the opening of your retrospective at the Museum of Modern Art. The gallery director left 4 messages asking to confirm your attendance.
I haven't decided yet. We'll see about that later.
Okay.
What else?
Just your usual fan mail. I've already answered.
Any news from Leo?
No, Carl. I can call him if you like.
No. No, don't bother. I'm starving.
Well, your breakfast is ready. Bacon and eggs, just the way you like them.
Thank you, Marcus.
You're welcome.
I would like to have my breakfast before noon, if you don't mind.
Video games.
Thank you, Marcus. Television.
Tensions continue to rise in the Arctic since Russia unilaterally declared the region part of its national territory. Several Russian warships have taken position in the Barents Sea since Saturday, and the Russian flag now flies over the ice field. The Russian president repeated in a speech...
Why don't you find something to do while I finish my breakfast?
Sure. Okay, Carl.
On the other hand, last night, the American ambassador again informed an emergency meeting of the UN that the United States would not accept this annexation under any circumstances. Several American destroyers are reported to be headed for the Barents Sea. Douglas Cornwall, chairman of the UN, announced at a press conference that we have never been so close to a third world war. He called on Russia and the United States to promptly renew talks before things get out of control.
Television off. Mankind is so depressing. Nothing but greed, stupidity, and violence. 5,000 years of civilization just to get to where we are. Something has changed in the way you play. Sometimes I think you have more humanity than most humans. One day I won't be here to take care of you anymore. You'll have to protect yourself and make your choices. Decide who you are and want to become. This world doesn't like those who are different, Marcus. Don't let anyone tell you who you should be. Let's go to the studio. Let's see where we left off. Remove the sheet. So, what's your verdict, Marcus?
Yes, there is something about it. Something I can't quite define. I guess I like it.
The truth is, I have nothing left to say anymore. Each day that goes by brings me closer to the end. I'm just an old man clinging to his brushes.
Carl.
But enough about me. Let's see if you have any talent. Give it a try. Try painting something.
Paint? What would I... Painting what?
Anything you want. Give it a try. That is a perfect copy of reality. The painting is not about replicating the world. It's about interpreting, improving on it, showing something you see.
Carl, I don't think I can do that. It's not in my program.
Go on, go. Try it. Grab that canvas. Do something for me. Close your eyes. Close your eyes. Trust me. Try to imagine something that doesn't exist, something you've never seen. Now concentrate on how it makes you feel, and let your hand drift across the canvas. God.
Hey, Dad.
Leo. I didn't hear you come in.
No, I was in the neighborhood. I thought I'd stop by. It's been a while, right?
You all right? You don't look so good.
Oh, yeah, I'm fine. Hey, listen, I need some cash, Dad.
Again? What happened to the money I just gave you?
Well, it just goes, you know?
Yeah, you're on it again, aren't you?
No, I swear it's not that.
Don't lie to me, Leo.
What difference does it make? I just need some cash, that's all.
Sorry. The answer's no.
What? Why?
You know why.
Yeah, I think I do know why. You'd rather take care of your plastic toy here than your own son, right? Tell me, Dad, what's it got that I don't? Smarter, more obedient, not like me, right? But you know what? This thing is not your son. It's a fucking machine!
Leo, that's enough. Enough.
You don't care about anything except yourself and your goddamn paintings. You've never loved anyone. You never loved me, Dad. You never loved me.
Androids weren't allowed in here. What's your problem? Want to buy me a drink? That's what I thought.
Lieutenant Anderson, my name is Connor. I'm the android sent by CyberLife. I looked for you at the station, but nobody knew where you were. They said you were probably having a drink nearby. I was lucky to find you at the 5th bar.
What do you want?
You were assigned a case early this evening. A homicide involving a CyberLife android. In accordance with procedure, the company has allocated a specialized model to assist investigators.
Well, I don't need any assistance. Especially not from a plastic asshole like you. Just be a good little robot and get the fuck out of here.
Listen, I think you should stop drinking and come with me. It'll make life easier for both of us. I understand that some people are not comfortable in the presence of androids, but
I am perfectly comfortable. Now back off before I crush you like an empty beer can.
You know what? I'll buy you one for the road. What do you say? Bartender, the same again, please.
See that, Jim? Wonders of technology. Make it a double. Did you say homicide? You wait here. I won't be long.
My instructions are to accompany you to the crime scene, Lieutenant.
Listen, I don't give a fuck about your instructions. I told you to wait here, so you shut the fuck up and you wait here.
Josh Douglas for Channel 16. Can you confirm that this is a homicide?
I'm not confirming anything.
God, what happened there?
Have they said anything?
Typical DPD. They don't tell us shit.
Androids are not permitted beyond this point.
It's with me. What part of staying in the car didn't you understand?
Your order contradicted my instructions, Lieutenant.
You don't talk, you don't touch anything, and you stay out of my way. Got it?
Got it.
Evening, Hank. We were starting to think you weren't gonna show.
Yeah, that was the plan till this asshole found me.
So, you got yourself an android, huh?
Oh, very funny. Just tell me what happened.
We had a call around 8. The lieutenant hadn't paid his rent for a few months, so he thought he'd drop by, see what was going on. That's when he found the body. Jesus, that smell was even worse before we opened the windows. The victim's name's Carlos Ortiz. He has a record for theft and aggravated assault. According to the neighbors, he was kind of a loner. Stayed inside most of the time. They hardly ever saw him.
Stayed easy in. What more? Calling everybody out in the middle of the night. Could have waited till morning.
I'd say he's been there for a good 3 weeks. We'll know more when the coroner gets here. There's a kitchen knife over here. Probably the murder weapon.
Any sign of a break-in?
Nope. The landlord said the front door was locked from the inside. All the windows were boarded up. The killer must have gone out the back way.
What do we know about his android?
Not much. The neighbors confirmed he had one, but it wasn't here when we arrived. I gotta get some air. Make yourself at home. I'll be outside if you need me.
Each letter is perfect. It's way too neat. No human writes like this. Chris, was this written in the victim's blood?
I would say so. We're taking samples for analysis.
Oh, Jesus, what the hell are you doing?
I'm analyzing the blood. I can check samples in real time. I'm sorry. I should have warned you.
Okay, just don't put any more evidence in your mouth. You got it?
Got it.
Fucking hell, I can't believe this shit.
stabbed 28 times.
Yeah. Seems like the killer really had it in for him. Red ice. Seems our friend Carlos liked to party. Chris, I want full analysis on the narcotics.
Consider it done, Lieutenant. Hey, Mike, you finished taking samples there?
Yeah, that's it.
What's keeping the car? You should have been there a half hour ago.
Door was locked from the inside. Killer must have gone out this way.
There are no footprints apart from Officer Collins' size 10 shoes.
Well, this happened weeks ago. Tracks could have faded.
No, this type of soil would retain a trace. Nobody's been out here for a long time.
He's on his way. It won't be long now. Come on, guys, get a move on. We don't want to be here all night.
Don't worry. No one wants to stay here a minute longer than they have to.
Lieutenant, I think I figured out what happened.
Oh, yeah? Shoot, I'm all ears.
It all started in the kitchen.
There are obvious signs of a struggle. The question is, what exactly happened here?
I think the victim attacked the android with the bat.
That lines up with the evidence. Go on.
The android stabbed the victim.
So the android was trying to defend itself, right? Okay, then what happened?
The victim fled to the living room.
And he tried to get away from the android. All right, that makes sense.
The android murdered the victim with the knife.
Okay. Your theory's not totally ridiculous, but it doesn't tell us where the android went.
It was damaged by the bat and lost some therium.
Lost some what?
Therium. You call it blue blood. It's the fluid that powers androids' biocomponents. It evaporates after a few hours and becomes invisible to the naked eye.
Oh. But I bet you can still see it, can't you?
Correct.
Yeah. Hey, what are you doing with that chair?
I'm going to check something.
Gonna check something.
I was just defending myself. He was gonna kill me. I'm begging you. Don't tell him.
Connor, what the fuck is going on up there?
It's here, Lieutenant!
Oh, shit. Chris, Ben, get your asses in here now! Come on!
Todd? Dinner is ready.
Yeah, I'm coming.
This is where, my friend.
There wasn't much in the kitchen. I did what I could.
Life's funny. I lost my job because of androids. Then when I need somebody to take care of this goddamn house, what do? I go out and hire a fucking android. Joke. Of course, androids are so fucking wonderful. They never fail. They're never tired. Never sad. was so fucking perfect, they ruined my fucking life! What are you looking at? What's your fucking problem? Not the life you dreamed of, eh? Maybe you think this is easy. Maybe you think it's my fault we live in this fucking shithole. My fault your fucking mother took off. You should stop taking drugs, Todd. Sometimes you really scare me, Todd. Fucking bitch took off without a word. Fucking whore walked out on me for a fucking accountant! It's all your fault.
Daddy, no!
It's all your fucking fault! Get back here. Come back here. Come back here right now! Yes! It's all her fault. I know it's her fault. I gotta teach her. I gotta teach her a good fucking lesson. That's what she deserves. First, I need a little hit. You stay there. Don't you dare fucking move, or I'll bust you worse than last time. Took off without a word. I could have been happy. I could have had a family. But no! She didn't give a shit about how I felt. I did everything I could to make her happy. It just wasn't enough. I just wasn't good enough for her! Little fucking brat! Oh, it's all her fault! I gotta teach her some respect! Alice! Daddy's very mad! You deserve to be taught a good lesson! A good fucking lesson. Alice! Don't make me come and get you! It's all your fault! It's all your...
Please
Good,
stop,
Alice.
Daddy!
For your own good.
That's enough! Leave her alone.
What the fuck are you doing? Get out of here, that's an order. You hear me?
No! I want you to leave Alice alone.
You want? What do you mean you want? You don't want anything. You're just a goddamn piece of plastic. I think you got a problem. We need to fix that.
Watch out, Kara!
Come here, bitch.
Please stop! Leave her alone!
Do as I say! Alice, honey. Alice. Look. Daddy's wounded. Be a good little girl. Come help Daddy. You bitches. Come here. Come back here. You're mine. You're both mine.
Please stop! Stop!
Come back here!
That was by far the most boring party I've been to in the last 25 years. Every time I go to one of these, I ask myself, what the hell am I doing here? I hate cocktail parties and all the schmoozers that go there.
Well, it's a chance for all those people who admire your work to meet you.
Yeah. No one gives a damn about art. All they care about is how much money they're gonna make out of it. Come on, let's have a drink. Oh, the excitement of this whole thing has made me thirsty.
Scotch? Neat as usual?
Absolutely.
Okay, but you know what your doctor would say.
Yeah, well, he can kiss my ass. I'm old enough to choose my own medication. Did you leave the light on in the studio?
No, I'm sure I didn't.
Call the police.
Detroit Police, what's your emergency?
This is Carl Manfred's android at 8941 Lafayette Avenue. We've just returned home and found the lights on. There may have been a break-in.
A patrol car is on the way.
Let's go check it out. Marcus, no. I'm gonna come with you.
Leo! What are you doing? You refuse to help me, so I'm helping myself. It's crazy what some people pay for this shit.
Don't touch them.
Look, they're all gonna be mine sooner or later anyway. Just think of it as a down payment on my inheritance.
Marcus, get him away from there. Get him out of here.
Listen, you should go before things get worse.
All you ever do is tell me to go away. What's wrong, Dad? Not good enough for you? Not perfect, like this fucking thing?
That's enough! Get out! Right now!
What makes it so special anyway, huh? What's it got that I don't?
Leave him alone!
Come on, let's see what you got!
Marcus, don't defend yourself, you hear me? Don't do anything.
Go ahead, hit me. What you waiting for? Think you're a man? Act like one.
Stop it!
What's the matter? Too much of a pussy?
Stop it, Leo! Stop it!
Too scared to fight back, you fucking bitch!
No.
That's right, I forgot you're not a real person. You're just a fucking piece of plastic.
Oh, Leo, leave him alone!
I'm gonna destroy you. And it'll just be me and my dad. I'm gonna tear you apart, and nobody's gonna give a shit. You know why? Because you're nothing. You hear me? You're nothing.
Carl, no! Oh, Carl.
Humans. Fragile machines.
Carl, don't leave, okay? Please don't go. Don't leave.
Remember, Marcus, don't let anybody tell you who you are.
No. No. Dad. No. Please.
This is all your fault. This never would have happened if it weren't for you. The android. Who's the android?
Why'd you kill him? What happened before you took that knife? How long were you in the attic? Why didn't you even try to run away? Say something, goddammit! Fuck it. I'm out of here. We're wasting our time interrogating a machine. We'll get nothing out of it.
You could always try roughing it up a little. After all, it's not human.
Androids don't feel pain. You would only damage it, and that wouldn't make it talk. Deviants also have a tendency to self-destruct when they're in stressful situations.
Okay, smartass. What should we do then?
I could try questioning it.
What do we have to lose? Go ahead. Suspect's all yours.
Game is like OC with consequences.
My name is Connor. What about you? What's your name? You're damaged. Did your owner do that? Did he beat you? Listen. I know you've been through a lot, but you need to help me understand what happened. Listen, I'm on your side. I want to help you, but there's nothing I can do if you won't talk to me. I'm here to help you, but you've got to trust me. All I want is to get you out of here.
What are they gonna do to me? They're gonna destroy me, aren't they?
They're going to disassemble you to look for problems in your biocomponents. They have no choice if they want to understand what happened.
Why did you tell them you found me? Why couldn't you just have left me there?
I was programmed to hunt deviants like you. I just accomplished my mission.
I don't want to die.
Then talk to me.
I can't.
understand how you felt. You were overcome by anger and frustration. No one can blame you for what happened. Listen, I'm not judging you. I'm on your side. All I want is the truth. Confess and I'll protect you. I promise I won't let anyone hurt you. You leave me no choice. It resisted. I couldn't see anything. I'm not getting anywhere. I give up.
Chris, lock it up.
All right, let's go.
Leave me alone.
Don't touch me.
The fuck are you doing?
You shouldn't touch it. It'll self-destruct if it feels threatened.
Stay out of this, got it? The fucking android's gonna tell me what to do.
You don't understand. If it self-destructs, we won't get anything out of it.
I told you to shut your fucking mouth. Chris, you gonna move this asshole or what?
I'm trying. I can't let you do that. Leave it alone now.
I warned you, motherfucker. That's enough. Mind your own business, Hank.
I said that's enough.
You're not gonna get away with it this time.
Everything is all right. It's over now. Nobody's gonna hurt you. Please, don't touch it. Let it follow you out of the room, and it won't cause any trouble.
Thank you for using Detroit buses.
All right. End the line.
End of the line.
Yeah, you're gonna have to leave.
Wake up. We have to go. Gonna be okay? We'll find somewhere to spend the night. Come on, Alice, we've got to hurry. It's warm in here. You'll feel better in no time. Come on, let's go. Come on, let's go. A motel. Looks like we found a place to stay.
The light is green. You may now cross the road.
Alice, you're freezing cold.
I'm okay. I'm not so cold.
You look lost.
We have nowhere to go.
I know someone who can help you.
But that's on the other side of town. We need a place for tonight. Come on, Alice.
Thank you for using Detroit buses.
Look, the store is still open. Maybe we should go inside. At least you'll be out of the cold.
What do you want?
I'm with a little girl, and we have nowhere to go. Could you spare some money so we can get a room for tonight?
Shit. A homeless android? Ah, that's the best yet. Look, this is a convenience store, not the Salvation Army, okay? You better go if you're not gonna buy anything.
We need a place to stay. Do you know anywhere we could spend the night? An abandoned house. At least we'd be out of the rain.
Kara, I don't like this place.
I know. But it's just for one night, and no one will look for us here. There's nothing more this way. Come on, let's go back.
We're not going in?
We have to find $40 and get rid of this uniform. Or go somewhere else. There's no point going any farther. It looks abandoned. Stand back, Alice. It's dry inside, and nobody will find us here.
I don't want to sleep in there. Can't we find a better place?
Okay. We'll find somewhere better.
Are you all right?
Yes, it's just a scratch. Be careful. Don't worry, we're just having a look. Alice? Alice! Wait, what are you doing?
Visitors. Ralph doesn't like visitors. They're nasty. They may hurt Ralph.
We thought nobody was here. All we want is a place to spend the night.
Visitors are dangerous. Look what they did to Ralph.
You have nothing to worry about. We're not going to do you any harm. You have my word.
You must excuse Ralph. Ralph still finds it difficult to control himself. Sometimes his fear makes him do things he regrets. Ralph has seen some hard times. He's just so scared the humans will get him again. You can stay if you want. Ralph won't hurt you.
Okay. We'll just stay the night.
Come on! Come on! This way. Ralph has lived here since he ran away. Ralph never goes outside, so no one knows he lives here. Humans come in to squat from time to time, but, you know, Ralph just hides till he leaves. You can make yourself at home here. Ralph is gonna go into the other room. He would like to stay with you, but he has things to do.
It's just for one night, Alice. We'll find a better place tomorrow. Right. Let's see where you can sleep. Sit down and I'll start a fire. You can come to bed. I did what I could. It's not much, but at least you'll be warm.
Why didn't he ever love me? Why was he always so upset with me? All I wanted was a life like other girls. Maybe I did something wrong. Maybe I wasn't good enough. That's why he was always so angry. I just wanted us to be a family. I just wanted him to love me. Why can't we just be happy?
I don't know, Alice.
You'll never leave me, right? Promise you'll never go.
I promise.
Will we be together forever?
Forever. You've got to sleep. Sleep tight, Alice.
place where we can be free. Find Jericho! Find Jericho!
want to live anymore. No, please. Don't leave me. Don't leave me!
Hello. I'm an AK-700 android. I was designed to serve you. What can I do for you? Hello. I'm an AK-700 android. I was designed to serve you. What can I do for you? Hello.
My program has detected an anomaly. Please contact the nearest CyberLife Maintenance Center.
Hello, Amanda.
Connor, it's good to see you. Finding that deviant was far from easy. You showed great skill in your investigation. But you knew deviants could be unstable. You should have been more cautious.
I thought I could make it talk. It was a judgment error.
Never mind. I'm sure you'll be more careful in the future. The interrogation seemed challenging. What did you think of the deviant?
It showed signs of PTSD after being abused by its owner. As if its original program had been completely replaced by new instructions.
This Lieutenant Anderson has been officially assigned to the deviancy case. What do you make of him?
I think he's irritable and socially challenged. But I also think he used to be a good detective. He's an intriguing character.
Unfortunately, we have no choice but to work with him. What do you think is the best approach?
I will adapt to his personality. It is in the best interest of the investigation that I avoid conflict and try to accommodate his psychology.
More and more androids show signs of deviancy. There are millions in circulation. If they become unstable, the consequences will be disastrous. You're the most advanced prototype CyberLife has ever created. If anyone can figure out what's happening, it's you.
You can count on me, Amanda.
Hurry, Connor. There's little time.
Can I help you?
I'm here to see Lieutenant Anderson.
Do you have authorization?
Yes.
Lieutenant Anderson hasn't arrived yet, but you can wait at his desk.
You might be in
Tensions in the
shock.
Arctic have reached a
take
new
it easy.
level, with a Russian carrier and an American patrol boat reported to
mind
have
getting me some
clashed
water,
last
please?
night. Several warning shots were exchanged, apparently with no damage or casualties to either side. The Minister for Defense, Dennis Riggs, has spoken of
you go.
intolerable provocation that cannot go unanswered.
I needed that.
The countries in the region, particularly Sweden and Canada,
Shouldn't be
have
too
called
long
for military forces to withdraw and an international conference to be held. So far, there has been no response from either Moscow or Washington. We'll keep you informed minute by minute as the situation develops.
It's okay. Relax. Just tell me what happened. Any little detail can catch the eye in a moment.
You and you, come with me.
Excuse me. Do you know what time Lieutenant Anderson usually arrives?
Depends on where he was the night before. If we're lucky, we'll see him before noon.
Thanks.
Hi, honey. You okay? Listen, I told you not to call me last night.
K9 unit required for stop and seizure at Detroit Central Station.
Be silly. Of course I want to see you. Baby, listen, I can't...
Call Hank Anderson.
Hi, this is Hank. Not here at the moment. You can leave a message if that's what turns you on, but don't expect me to call back. Beep. Whatever.
Lieutenant Anderson, this is Connor. I'm the android sent by CyberLife. It's almost noon, and I'm waiting for you at the office. It's good to see you again, Lieutenant.
Oh, Jesus.
Hank! In my office. I've got 10 new cases of androids on my desk every day. We've always had isolated incidents. Old ladies losing their android maids and that kind of crap. But now, we're getting reports of assaults and even homicide, like that guy last night. This isn't just CyberLife's problem anymore. It's now a criminal investigation, and we've got to deal with it before the shit hits the fan. I want you to investigate these cases and see if there's any link.
Why me? Why do I gotta be the one to deal with this shit? I am the least qualified cop in the country to handle this case. I know jack shit about androids, Jeffrey. I can barely change the settings on my own phone.
Everybody's overloaded. I think you're perfectly qualified for this type of investigation.
Bullshit! The truth is, nobody wants to investigate these fucking androids, and you let me hold in the bag.
CyberLife sent over this android to help with the investigation. It's a state-of-the-art prototype. It'll act as your partner.
No fucking way! I don't need a partner, and certainly not this plastic prick.
Hank, you are seriously starting to piss me off. You are a police lieutenant. You are supposed to do what I say and shut your goddamn mouth.
You know what my goddamn mouth has to say to you?
Okay,
huh?
Okay. I'll pretend like I didn't hear that, so I don't have to add any more pages to your disciplinary folder, because it already looks like a fucking novel. This conversation is over.
Jeffrey, Jesus Christ, why are you doing this to me? You know how much I hate these fucking things. Why are you doing this to me?
Listen, I've had just about enough of your bitching. Either you do your job or you hand in your badge. Now, if you'll excuse me, I've got work to do.
I won't keep you any longer. Have a nice day, Captain.
But we are blinded by something called shot noise.
Shot noise is the direct manifestation of the phase uncertainty of the vacuum state. When those vacuum fluctuations enter the detector, they alter the precise timing, the phase of the photons in the main laser beam.
Because the laser isn't a continuous fluid, right?
Exactly. The laser isn't a perfectly continuous fluid of energy. It is composed of individual, discrete quanta, photons.
So it's a matter of Poisson's statistics. The arrival of photons at the photodetector isn't perfectly spaced out like cars on a carefully regulated assembly line. Because of the quantum phase uncertainty, they arrive randomly. Some milliseconds you get a big cluster of photons, some milliseconds you get a lull.
The very common analogy is listening to rain on a tin roof, but we can make it more precise. Imagine you were trying to measure a very fast, high-frequency acoustic signal, like a rapid drum roll. But the instrument you're using to measure it is being pelted by a hailstorm.
Okay, I can picture that.
If you are measuring over a long period of time, The randomness of the hail sort of averages out into a steady background hum, but because you are trying to detect a high-frequency drum roll, you have to sample the sound over extremely short time intervals.
And in those microscopic time intervals, the statistical variance of the hail strikes, the Poisson distribution of the photon arrivals, is massive. The randomness of the photons hitting the detector completely drowns out the fast, tiny flickers of light caused by the high-frequency gravitational wave.
That is shot noise. The fundamental discreteness of light masks the high-frequency chirps. So the logical experimental fix is to just turn up the laser power.
Right. If you flood the detector with an overwhelmingly massive number of photons, the relative statistical variance of their arrival times shrinks.
You turn the hailstorm into a massive waterfall. The flow becomes much smoother relative to the total volume, and the shot noise drops.
Which sounds like a great solution until we look at the low frequencies. The early and spiral phase of the black holes before they hit the ISCO generates slow, low-frequency gravitational waves. If we crank up the laser power to fix the high-frequency shot noise, we trigger the second head of the monster, radiation pressure noise.
Right. If shot noise is caused by phase uncertainty, radiation pressure noise, or RPN, is the direct physical consequence of amplitude uncertainty. This brings us back to the fact that light actually carries physical momentum.
Right. When a photon strikes one of those 40-kilogram suspended glass mirrors and reflects back, it imparts a tiny physical kick to the mass.
It's P equals E over C. The momentum equals the energy divided by the speed of light. Now, because of the amplitude uncertainty of the vacuum state, the absolute number of photons hitting the mirror at any given instant is constantly fluctuating.
It's not a steady push.
No, it creates a fluctuating, random physical force on the mirrors.
It's like a barrage of microscopic quantum BBs just randomly striking the glass.
And this random physical shoving is devastating at low frequencies. The mirrors are suspended as pendulums. A 40-kilogram pendulum is incredibly massive, so it has immense inertia. If you hit it with a high-frequency, rapid-fire vibration, the mass simply cannot respond fast enough. It basically stays still.
So at high frequencies, this radiation pressure noise isn't really an issue.
But pendulums are highly susceptible to slow, low-frequency forces.
Precisely. The random quantum kicks from the fluctuating amplitude of the light actually cause the macroscopic 40-kilogram mirrors to slowly drift and swing back and forth.
Yeah, and this physical motion of the mirrors flawlessly mimics the slow stretch and squeeze of a low-frequency gravitational wave.
That's terrifying. The universe is literally faking a gravitational wave signal by shoving our mirrors with the uncertainty of nothingness.
It is the ultimate frustration for an experimental physicist.
Okay.
You are caught in a vicious trap. If you increase the laser power to smooth out the statistical arrival times and reduce the high-frequency shot noise, you are simultaneously increasing the total number of photons bouncing off the mirrors, which violently amplifies the physical kicking.
You reduce the shot noise, but you massively increase the radiation pressure noise.
You are totally trapped by Heisenberg.
And the sources detail the mathematics of this exact trap. They provide an equation for the radiation pressure noise spectrum, denoted as S sub RPN, which scales directly with the laser power P and inversely with the mirror mass M and the frequency omega cubed.
Wow.
For the specific parameters of advanced LIGO, utilizing those 40-kilogram mirrors and its standard operating laser power, the exact point where the low-frequency radiation pressure noise perfectly equals the high-frequency shot noise is 43 hertz.
That 43 hertz mark is the crossover. Above 43 hertz, the high-frequency phase uncertainty blinds you. Below 43 hertz, the low-frequency amplitude uncertainty physically shoves your detector around. And you cannot change the laser power without sacrificing one end of the spectrum for the other.
We can't change the laser power. We can't easily change the mass of the mirrors. We seem entirely stuck. But, we wouldn't be doing this deep dive if physicists just gave up.
Thankfully, they didn't.
We can't break the laws of quantum mechanics. We can't make the h-bar over 2 uncertainty disappear. But we can sculpt it. So how do we bypass this roadblock?
We use quantum optics to literally change the shape of the vacuum. This is the concept of squeezing.
Squeezing.
The Heisenberg uncertainty principle dictates that the product of the phase uncertainty and the amplitude uncertainty must be greater than or equal to h-bar over 2. But crucially, it does not mandate that the variance in phase and the variance in amplitude must be equal to each other.
So the vacuum state is a symmetrical circle in phase space, but we can squash that circle.
Exactly. We can artificially reduce the variance in one property, let's say the phase, to a level far below the standard quantum limit. We mathematically and physically squeeze the uncertainty out of the phase.
But to satisfy Heisenberg, that uncertainty has to go somewhere.
Right. So as a direct consequence, the variance in the orthogonal property, the amplitude, violently increases. The circle becomes an elongated ellipse.
We accept massive ignorance in one parameter to gain extreme precision in the other, but how do you actually do that in a laboratory? You don't just put empty space in a vice grip.
No, the sources outline the engineering required, and it revolves around an optical parametric oscillator, or OPO. Inside this device is a nonlinear optical crystal.
Okay, let's walk the students through the mechanism here. How does a crystal squeeze the phase of a vacuum?
The underlying physical process is called spontaneous parametric downconversion. In a standard linear material like normal glass, a photon goes in and a photon comes out. But in a nonlinear optical, crystal-like periodically poled potassium titanal phosphate, the atomic lattice interacts with light in a very specific, energy-conserving way.
We pump this crystal with a secondary Brate laser operating at a high frequency, right?
But typically green light in these setups, which is twice the frequency of the main infrared LIGO laser.
Yes.
As this high-energy pump laser passes through the nonlinear medium, occasionally the structure of the crystal will cause one of those high-energy green photons to spontaneously split or downconvert into a pair of lower-energy infrared photons.
And this is where the quantum magic happens. Those two new photons are not independent. Because they were born from the exact same parent photon, their properties are fundamentally correlated. They are quantumly entangled.
Precisely. Now, recall that the vacuum of empty space, the random fluctuations, is constantly entering this crystal at all frequencies. As the Brate pump laser drives the downconversion process, it interacts with these vacuum fluctuations.
Okay.
The crystal essentially forces the random, uncorrelated vacuum photons to be replaced by the highly correlated entangled pairs it is generating.
The source material uses a very specific evocative phrase to describe this. It says the down conversion process makes the photons arrive more regularly, as if the photons are holding hands rather than traveling independently.
I love that phrase.
I think it's a brilliant way to visualize it. Because they are entangled, their timing, their phase, is no longer governed by pure random Poisson statistics.
Their arrival times are correlated, they are paired up, and because their timing is highly structured, the variance in the phase of the electromagnetic field drops drastically. We have successfully squeezed the phase uncertainty of the vacuum state.
And the texts quantify this using a specific mathematical term, the squeeze factor, written as e to the 2r. The factor r is the squeezing parameter.
Yes. The mathematics of squeezing are incredibly elegant. If you inject this squeeze vacuum state into the dark port of the LIGO interferometer, the effect on the phase measurement is exactly the same as if you had mathematically multiplied the power of the main laser by a factor of e to the 2r.
It's basically an optical cheat code. We get the massive statistical smoothing of a vastly more powerful laser, but without actually having to build a laser that would melt the physical glass of the mirrors.
The shot noise drops dramatically, clearing up the high-frequency detection band. It seems like the perfect solution.
It does seem perfect, until you remember the other half of Heisenberg.
Let's talk about the balloon animal analogy.
Oh, this is the painful part.
Yeah. If you take a long balloon, representing the total area of our quantum uncertainty, and you squeeze the middle of it tightly with your hand, representing our reduction in phase noise, that middle section becomes incredibly narrow and precise. But the air inside the balloon has to go somewhere. The ends of the balloon violently bulge out.
Because the area of the ellipse must remain constant. So here is the brutal reality. By squeezing the phase to eliminate the high-frequency shot noise, we have forced the amplitude uncertainty to become massive. But the amplitude uncertainty is what dictates the random fluctuations in photon momentum. Doesn't that mean we are violently increasing the radiation pressure noise?
Yes, it does.
If the amplitude variance is huge, aren't we basically hitting those 40-kilogram mirrors with quantum cannonballs instead of quantum BBs?
You have just hit the exact wall that experimentalists faced for a decade. What you were describing is standard, frequency-independent squeezing, and it does exactly what you fear. It beautifully cleans up the high frequencies where shot noise dominates.
With the low frequencies.
Right, because the amplitude uncertainty is expanded massively, the random force on the mirrors at low frequencies becomes catastrophic. The mirrors swing wildly, entirely drowning out the low-frequency gravitational waves from the early in-spiral phase.
We fixed the high pitch, but we completely destroyed the low pitch. The texts explicitly call this degradation anti-squeezing.
Yes. If you use standard squeezing, you haven't solved the whack-a-mole problem. You've just amplified it. You are trading a slight improvement in measuring the ISCO plunge for total blindness of the preceding inspiral.
Which brings us to the true masterstroke of modern physics. The engineering marvel that this entire deep dive has been building toward. We cannot squeeze the light the same way at every frequency. We need a system that knows when to squeeze the phase and when to squeeze the amplitude.
We need frequency-dependent squeezing.
Right, so how do we do that?
Well, to conceptualize this, we return to phase space. We define a squeeze angle, denoted by the Greek letter phi. The angle of the ellipse in phase space dictates which physical property is being squeezed and which is being anti-squeezed.
So if the ellipse is oriented horizontally, you are squeezing amplitude. If it's oriented vertically, you are squeezing phase.
Exactly. Our goal is to dynamically rotate that ellipse, that angle phi, depending on the frequency of the noise, which we'll call omega.
Okay, so we want the quantum state to be phase squeezed, vertically oriented at the high frequencies where shot noise dominates. But as we move down the spectrum below 43 hertz, we want that ellipse to physically rotate 90 degrees to be amplitude squeezed, horizontally oriented, so that we suppress the violent kicks of the radiation pressure noise.
We need to squeeze the middle of the balloon for the fast high pitches and squeeze the bulging ends of the balloon for the slow low pitches.
But rotating a quantum state on the fly based on its frequencies sounds like a violation of causality. How does the vacuum know what frequency it is interacting with?
This is where the physics is just so beautiful. The solution relies on a profoundly simple wave mechanic mentioned in the sources. A phase-squeezed vacuum state and an amplitude-squeezed vacuum state are physically the exact same thing, just delayed by a quarter of a wave cycle.
Wait, really?
Hey, take a look at these samples yet? Lab report says they cut it with something. Maybe they're trying out a new form of red ice. We really need the forensics. All right, I'll chase it up. Take a look at these samples yet? Lab report says they cut it with something. Maybe they're trying out a new form of red ice. We really need the forensics. All right, I'll chase it up. Hey, take a look at these samples yet? Lab report says they cut it with something. Maybe they're trying out a new form of red ice. We really need the forensics. All right, I'll chase it up. See samples yet? Lab report says they cut it with something. Maybe they're trying out a new form of red ice. We really need the forensics. All right, I'll chase it up.
It's an honor to be working with you, Lieutenant. I'm sure we'll make a great team. In any case, I'd like you to know I'm very happy to be working with you. I'm sure we'll make a great team. Now that we're partners, it would be great to get to know each other better. Is there a desk anywhere I could use?
No one's using that one.
You have a dog, right?
How do you know that?
The dog hair's on your chair. I like dogs. What's your dog's name?
What's it to you? Sumo. I call him Sumo.
You're a Detroit Gears fan, right? Denton Carter scored 53% of his shots from the three-point line yesterday. Did you see the game?
That's what I was watching at the bar last night.
Oh. A lot of people don't appreciate having androids around. I was wondering, is there any reason in particular you despise me?
Yeah. There is one.
If you have any files on Deviants, I'd like to take a look at them.
Terminal's on your desk. Knock yourself out.
Have you known Captain Fowler for long?
Yeah. Too long.
I was wondering, do you always arrive at the office at this time?
I arrive when I arrive. Stop busting my balls, okay?
243 files. First dates back 9 months. It all started in Detroit and quickly spread across the country. An AX-400 is reported to have assaulted a man last night. That could be a good starting point for our investigation. I understand you're facing personal issues, Lieutenant. But you need to move past them, and...
Hey, don't talk to me like you know me. I'm not your friend, and I don't need your advice, okay?
I've been assigned this mission, Lieutenant. I didn't come here to wait until you feel like working.
Listen, asshole. If it was up to me, I'd throw the lot of you in a dumpster and set a match to it. So stop pissing me off. Or things are gonna get nasty.
Lieutenant, sorry to disturb you. I have some information on the AX-400 that attacked the guy last night. It's been seen in the Ravendale district.
I'm on it.
That's all for now. Free to go.
We've got officers sweeping the neighborhood in case anybody saw anything.
Okay, well, let me know if they turn anything up.
What are you gonna do with that?
I have no idea.
It took the first bus that came along and stayed at the end of the line. Its decision wasn't planned. It was driven by fear.
Androids don't feel fear.
Deviants do. They get overwhelmed by their emotions and make irrational decisions.
All right, well, that still doesn't tell us where it went.
It didn't have a plan, and it had nowhere to go. Maybe it didn't go far.
Maybe.
Ralph found this to feed the little girl. It's good for her. A present. To make up for past misunderstandings. Ralph will cook. We will do just like humans do. Humans like burnt meat. Come. Come and sit down.
That's very kind of you, Ralph. But we have to go.
Go? No, you will go once the little girl is eaten. We will eat together, just like a family. You know, the father, the mother, and the little girl.
No, Ralph. We're leaving now. Come on, Alice.
The little girl's going nowhere.
You're not going to hurt her, are you? We're friends. Remember?
No, Ralph doesn't want to hurt the little girl. He just wants her to eat. That's all.
Humans don't eat that, Ralph.
Wrong! Humans eat dead animals, I know that.
Okay. We'll eat together. Like a family.
That's better. Ralph went to a lot of trouble to find something for the little girl to eat. It wouldn't be polite for her to refuse, would it? Great. Be great. Succulent, you'll see. Succulent. Succulent. Father, mother, little girl.
Please, Connor. I don't want to eat that.
What did she say?
She said she can't wait to eat it. She's very hungry.
The little human is not going to regret it. Ralph found the best, the biggest one he could find. This is going to be succulent. Succulent. Go ahead. Eat.
I saw the body upstairs. You killed that human, didn't you?
No. No, he was like that when Ralph found him.
You said you wanted to be like a family, Ralph. Father, mother, the little girl, remember? Father would never threaten his little girl with a knife to make her eat.
Ralph went to a lot of trouble. That's why. He just wanted the little girl to eat. Ralph is not bad. No, not bad.
Then let us go.
Anybody home? There's blue blood on the fence. I know another android was here. Don't be afraid. I'm not gonna hurt you. I'm looking for an AX-400. Have you seen it?
Ralph's seen nobody.
Are there any other androids here?
Other androids? No. Ralph is alone.
There's blue blood on the fence. I know another android was here.
Ralph scratched himself coming through. That's Ralph's blood.
Is anyone upstairs?
No. Nobody.
Coming, Lieutenant!
Connor, the fuck are you doing? Did you find something?
No. No, it's not here.
Yeah, just like I said in the first place. Come on, let's get out of here.
Thanks.
Protect the little girl. The humans must not find her.
Several sources report that CyberLife has provided Detroit police with a prototype detective android. Although police assistant androids have existed for several years now, this would be the first case of an android being authorized to play an active role in criminal investigations. We contacted CyberLife for comment, but no longer.
We are now approaching Ferndale Station. Please take care of stepping onto the platform. Customers are reminded that all androids must ride in the designated area.
There's a place where we can be free. Find Jericho.
They missed her. You spare some change? Not surprised. Apparently she did. Yeah. I know. It's crazy, right?
I heard that android boy bat's gonna win some music prize.
You mean here for you? You're so pretty.
My kid's almost dead. Anything else?
Oh, sorry. Excuse me.
Space occupied. Welcome to Android Parking. Are we really going to get rid of Mandy?
hear about that artist, Carl Manfred?
Yeah, kinda sad.
I heard his android killed him.
Where'd you hear that?
I read it somewhere.
Well, don't believe everything you read.
I don't need much, just enough for a cup of coffee.
Spare some change?
Hey, I don't need much, just enough for a cup of coffee.
so hungry. If I could just get some food. the money.
The light is green. You may now cross the road.
Just enough for a cup of coffee.
So, what did he say? Say so. change?
Hey, listen, can you spare some cash? Hey, man, can you help me out? I don't need much, just enough for a cup of coffee.
Do you know where Jericho is?
Hey, listen, can you spare some cash? Hey, ma'am, can you help me out?
Welcome to Jericho.
Really? Just a delay?
That is the secret. Phase and amplitude are mathematically orthogonal properties. If you take a wave that is squeezed entirely in its phase, and you simply delay its propagation by a quarter of its wavelength, a pi over 2-phase shift, it transforms perfectly into a wave that is squeezed in amplitude.
Oh, wow. So the entire challenge of rotating the quantum ellipse boils down to introducing a frequency-dependent delay. We need a device that takes the incoming phase squeezed vacuum, looks at the low frequencies and delays them by a quarter cycle, but looks at the high frequencies and lets them pass through without any delay at all.
Exactly. And the device they built to accomplish this is a massively long optical cavity, known as a filter cavity. In the design implemented for advanced LIGO, this cavity is a 300-meter-long vacuum tube with highly reflective mirrors at both ends.
Basically a giant Fabry-Perot interferometer used purely as a delay line. A 300-meter tube, just to delay nothingness. Let's break down exactly how a tube delays low frequencies but not high frequencies, because this is the crux of the engineering. The text states the cavity is intentionally detuned from the main laser's carrier frequency. What does detuning physically mean here?
To understand detuning, you have to understand resonance. A cavity has a resonant frequency based purely on its physical length. If the wavelength of the light fits perfectly into the distance between the mirrors, the light resonates. It builds up inside the cavity, bouncing back and forth many times before eventually reflecting back out.
Right.
But if the cavity is detuned, it means the physical distance between the mirrors has been slightly adjusted so that the main carrier frequency of the laser does not fit perfectly.
It's off resonance. So when the main carrier frequency hits the cavity, it doesn't enter and bounce around. It just immediately bounces off the front mirror.
Correct. But we are not just dealing with the carrier frequency. The quantum noise, the vacuum fluctuations, enters the cavity as sidebands. In the frequency domain, any fluctuation or signal is mathematically represented as an upper sideband at a higher frequency than the carrier, and a lower sideband at a lower frequency than the carrier.
So a 100 hertz noise fluctuation is represented as light, that is exactly 100 hertz above the carrier frequency, and 100 hertz below the carrier frequency.
Precisely. And because the cavity is detuned, its resonant peak is shifted away from the carrier. This creates an asymmetry. The upper sideband and the lower sideband are now at different distances from the cavity's resonant frequency.
This is the genius of it. Because they are at different distances from the resonance peak, they interact with the cavity differently.
Exactly. The sideband that is closer to resonance will enter the cavity, bounce back and forth a few times, and be delayed. The sideband that is further from resonance will bounce off more quickly. The 300-meter filter cavity applies a differential phase shift to the upper and lower sidebands.
And as the source text explicitly outlines, the squeezed quadrature angle, or angle phi, the orientation of our quantum ellipse, is determined entirely by the relative phase between those upper and lower sidebands.
Yes. By applying that differential phase shift through the detuned resonance, the cavity is physically rotating the orientation of the quantum uncertainty ellipse in phase space.
That's incredible.
The sources highlight a specific study where researchers actually mapped this out. They used quantum tomography to reconstruct the Wigner function, which is the actual phase space probability distribution of the state. They demonstrated that reflecting the squeeze state off the cavity physically rotated the Wigner function by 39 degrees.
Which allowed them to reduce the noise by up to 5.5 decibels along that specific newly rotated axis.
It is a phenomenal demonstration of controlling macroscopic quantum mechanics. The 300-meter cavity naturally and passively provides the exact frequency-dependent delay needed.
High frequencies bounce off quickly and remain phase squeezed to combat shot noise.
And low frequencies linger in the cavity, undergo a quarter-wave delay, rotate 90 degrees, and emerge amplitude squeeze to suppress radiation pressure noise.
It's like engineering a dynamic, perfectly tuned shock absorber for a car, but made out of light. The shock absorber knows instantly that a sudden high-frequency speed bump requires a stiff response to absorb the phase noise, but a slow, low-frequency pothole requires a soft, yielding response to absorb the amplitude noise. We are taking the fundamental shape of quantum uncertainty, and we are rotating it on the fly depending on what pitch of gravitational wave we are trying to hear.
It is arguably one of the most elegant, holistic solutions in modern physics. By reflecting the squeeze state off this detuned filter cavity before injecting it into the main LIGO interferometer, the total quantum noise across the entire detection band, from the slow and spiral to the violent ISCO plunge, can be minimized.
And the math in the text points out that the noise is reduced to e to the negative 2 times the standard quantum limit.
Which is mathematically analogous to simultaneously increasing the laser power to eliminate shot noise and increasing the physical mass of the 40-kilogram mirrors by a factor of e to the 2r, so they don't get kicked around by the radiation pressure.
We get the physics-breaking benefits of an impossibly powerful laser and impossibly heavy mirrors without having to build either.
It's pure, brilliant physics. But, as we transition from the theory to the actual experimental results, we have to acknowledge the brutal reality of optics.
The catch.
Always a catch. The universe does not want to remain squeezed. The quantum states we are creating are unimaginably fragile. Implementing this in the physical world is a constant fight against optical loss.
We need to define exactly what loss means in the context of quantum squeezing. Because for a normal laser beam, optical loss just means the beam gets a little dimmer, right? A piece of dust on a mirror scatters 1% of the light, so you only have 99% of the power. It's annoying, but it doesn't destroy the nature of the light. But with squeezing, optical loss is catastrophic.
It is entirely destructive. Remember the mechanism of squeezing. The nonlinear crystal created entangled pairs of photons. They're holding hands. Their phases are perfectly correlated, which is what squashes the uncertainty circle into an ellipse.
But what happens when the beam hits a microscopic imperfection on a mirror, or gets absorbed by a molecule of residual gas, and one of those entangled photons is lost?
When a squeezed photon vanishes, nature abhors the vacuum. Literally, you cannot have an empty slot in the electromagnetic field. The instant that correlated photon is lost to scattering or absorption, an unsqueezed, normal, random vacuum fluctuation instantly sneaks in from the surrounding environment to take its place in the beam.
The hiss comes back.
Instantly. Every time you lose a correlated photon, a random, noisy, independent photon steps into the line. The perfect correlation is broken. The beautifully narrow quantum ellipse puffs back out toward a standard, noisy circle. This effect is mathematically modeled like a beam splitter. If your system has 10% optical loss, it acts mathematically identically to passing your perfectly squeezed beam through a 90-10 beam splitter, where the open port is constantly injecting raw, noisy vacuum back into your signal.
So the loss sets a hard, impassable physical limit on the improvement that squeezing can offer. And the sources give us the exact, painful numbers on this battle.
Yeah, the generation of the squeezing inside the optical parametric oscillator is actually incredibly efficient. The nonlinear crystal can routinely generate a massive 20 decibels of squeezing. The quantum ellipse is squashed incredibly thin.
But then that fragile state has to travel through the physical optical system to get to the main interferometer.
And it pays a massive toll at every single glass surface.
Let's look at the frequency-independent losses the text breaks down. First, there's a 3% loss just in the fundamental generation inside the OPO cavity itself. Then the light has to pass through Faraday isolators. These are magnetic optical devices necessary to prevent stray light from reflecting backward and destroying the squeezing crystal.
But Faraday isolators are complex and slightly absorptive. The design requires the light to pass through them 3 times, with a 0.8% loss on each pass.
Then we have mode matching. The physical spatial shape of the squeezed beam has to perfectly overlap with the spatial shape of the main LIGO laser beam. Any light that doesn't perfectly overlap is technically lost to the system.
Right.
The mode matching into the output mode cleaner incurs a 1% loss. The mode matching into the actual main interferometer incurs another 1% loss, and there is an additional 1% loss just trying to mode match the beam into the 300-meter filter cavity.
It is a relentless death by 1,000 cuts. If you sum all of those up, the text notes a total frequency-independent loss of roughly 9%.
Which honestly doesn't sound terrible to a layperson. Getting 91% of your signal through sounds like an A- in engineering. But because of the devastating way vacuum replacement works, how much of our original 20 decibels of squeezing actually survives that 9% loss?
It drops precipitously. because the unsqueezed vacuum floods back in at every 1% loss point. Starting from 20 dBAs of pure squeezing inside the crystal, those cumulative losses reduce the actually observed squeezing at the detector down to roughly 9 to 10 decibels.
More than half the squeezing factor is completely destroyed just moving the light a few meters across the optical table.
And that devastating drop is just from the frequency-independent losses. That doesn't even account for the frequency-dependent losses inside the 300-meter filter cavity itself.
Exactly. Because the filter cavity works by trapping the low frequencies and forcing them to bounce back and forth to create that quarter-wave delay. Those specific low frequencies spend vastly more time interacting with the mirror coatings.
More bounces mean more chances for microscopic scattering and absorption.
So the low frequencies, which are already struggling, suffer even higher loss rates inside the cavity, pulling the observed squeezing down even further.
It is a brutal, agonizing fight for every fraction of a decibel. But, despite the extreme fragility of the quantum state, despite the constant bombardment of the environmental vacuum trying to puff the ellipse back out, the implementation of this technology is an undeniable triumph.
It really is. The sources present the ultimate benchmark goal for advanced LIGO using these technologies, referred to as Team Red sensitivity. When they finally lock the 300-meter cavity and inject the frequency-dependent squeezed light, what do the results look like?
Even after accounting for all the degradation, all the scattering, and all the mode-matching losses, the results are monumental. The injection of the dynamically rotated squeezed vacuum provides an overall confirmed improvement in the detector's sensitivity by a factor of 3 at all frequencies above 100 Hz.
The high frequencies. The shot noise is conquered, the ISCO plunge becomes crystal clear.
And crucially, the filter cavity performs exactly as designed. At the low frequencies below 100 Hz, it provides a sensitivity improvement of a factor of 3 to 4.
The radiation pressure noise is suppressed. The quantum BBs stop kicking the mirrors. The dynamically rotating shock absorber successfully absorbed the slow potholes without ruining the fast speed bumps.
It works. And if we extrapolate what a factor of 3 improvement across the board means for astrophysics, it completely rewrites the scale of observational astronomy.
Let's talk about that scale.
The standard metric astrophysicists use to evaluate a detector's capability is the binary neutron star in spiral range. This is a measure of exactly how far out into the universe we can confidently detect the collision of two standard mass neutron stars.
Before this technology, utilizing just raw laser power and fighting the whack-a-mole game, the range was approximately 200 megaparsecs.
With the full successful implementation of frequency-dependent squeezing, that in-spiral range is projected to leap from 200 megaparsecs to over 600 megaparsecs.
And this is where the geometry of the universe makes this achievement so staggeringly important. For the students listening, remember that we aren't pointing LEGO like a standard optical telescope. It doesn't look down a narrow tube at a specific patch of sky.
No, it's an omnidirectional microphone. It listens in 3 dimensions simultaneously.
If you increase the sensitivity by a factor of 3, you are increasing the radius of your listening sphere by 3. And the volume of a sphere scales with the cube of the radius.
Volume equals 4/3 pi r cubed.
Exactly. 3 to the third power is 27. By mastering the quantum vacuum, by utilizing a 300-meter detuned cavity to rotate the phase space of nothingness, we aren't just searching 3 times as much space. We are instantly searching a volume of the universe that is 27 times larger.
We are encompassing thousands upon thousands of new galaxies, millions of potential new black hole and neutron star collisions, entirely because we learned how to dictate the rules of empty space.
It is just an unbelievable arc of human ingenuity. Let's synthesize this entire journey for a second. We started deep in the realm of pure theoretical mathematics. We saw how physicists wrestled with the computationally impossible nonlinear chaos of general relativity 2, massive black holes warping spacetime and radiating energy.
And they solved it with the effective one-body mapping, using canonical transformations to pin one mass to the floor, reducing the two-body problem to a tiny test mass moving through a mathematically deformed background.
They calculated the precise post-Newtonian coefficients, like nu/2 for the spacetime drag, allowing them to map the exact threshold of the innermost stable circular orbit. They even proved the robustness of the map using first post-Minkowskian scattering for objects flying past each other at near light speed.
Right, they gave the experimentalists the perfect mathematical template of the high-frequency chirp.
But then the experimentalists hit the absolute limit of measurement, the Heisenberg uncertainty principle. Empty space wasn't empty.
The quantum hiss. The vacuum state presented a fundamental uncertainty in phase, which manifested as random, Poisson photon statistic shot, noise blinding our ability to see the fast ice go chirp.
And it presented an uncertainty in amplitude, which manifested as random physical momentum kicks radiation pressure, noise shoving our 40-kilogram pendulums around, and faking the slow and spiral waves.
A trap that crosses over at exactly 43 hertz.
But physicists bent the rules. They used nonlinear potassium titanal phosphate crystals to spontaneously downconvert pump lasers, forcing the vacuum photons to become entangled pairs, to hold hands. They squeezed the phase uncertainty down by a massive 20 decibels.
Which created the balloon animal problem.
Yeah.
Squeezing phase blew out the amplitude, anti-squeezing the low frequencies, and violently kicking the mirrors.
So they engineered the ultimate masterstroke, the 300-meter detuned filter cavity, taking advantage of the physics that a phase squeeze state is just an amplitude squeeze state delayed by a quarter wavelength.
They bounce the light into a cavity sitting just off resonance, applying a differential phase shift to the upper and lower sidebands.
Physically rotating the Wigner function 39 degrees in phase space, depending solely on the frequency of the light.
Creating frequency-dependent squeezing. Squashing the shot noise at high frequencies, rotating smoothly, and squashing the radiation pressure noise at low frequencies.
And surviving the brutal reality of optical loss and vacuum replacement to deliver a detector that searches 27 times more of the cosmos, it is a monumental scientific epic.
It truly is. And, as we conclude, I want to leave the listeners with a profound realization based on the implications of these source texts. Everything we have discussed today signifies a fundamental paradigm shift in physics. Gravitational wave observatories like LEGO have officially pushed humanity into the era of macroscopic quantum mechanics.
Right, because for the last century, quantum mechanics was entirely confined to the microscopic world. We studied the bizarre probabilistic behavior of single isolated electrons or microscopic photons or ultra-cold atoms in a vacuum trap. The prevailing thought was always that quantum weirdness simply didn't apply at the human scale.
But inside LIGO, that boundary has been erased. The objects at the heart of this machine are 40-kilogram cylinders of solid glass. They are human-sized, incredibly massive objects that you could literally wrap your arms around. And yet, their physical motion is no longer governed strictly by classical mechanics. Their trajectories are literally, physically being dictated by the quantum void popping into and out of existence. The fundamental uncertainty of the universe is strong enough to move macroscopic metal and glass.
That is just staggering to think about.
And we haven't just passively observed this. The engineers behind frequency-dependent squeezing have figured out how to actively sculpt that quantum void. They are using optical delay lines to physically grab the uncertainty of nothingness and rotate it, manipulating the fundamental probabilistic nature of reality itself just to build a better telescope.
It's the ultimate testament to scientific persistence. The universe is incredibly noisy. The fabric of space-time is muddy, fuzzy, and fundamentally uncertain at the quantum level. But if you are willing to spend decades doing the grueling mathematics, and if you are bold enough to build machines that literally reshape the empty space inside them, you can cut through the hiss.
You can sculpt the uncertainty.
And you just might hear the echo of two black holes colliding a billion light years away.